Where does the universe truly end? In space or in time? How can light itself serve as our time machine into the cosmic past? What do redshift and expansion reveal about the shape and fate of the cosmos? The idea of an edge to the universe is surprisingly subtle. At first, one might imagine a physical boundary or wall, but cosmologists mean something else entirely. Because light travels at a finite speed, and the universe has a finite age, there exists a sphere around us, beyond which even the fastest photon has not had time to reach us. This edge is not a surface you could touch. It is a horizon in time, a limit set by the interplay of light speed and cosmic age, and as the universe grows older, that horizon grows with it. The region encompassed by this horizon is called the observable universe. If the cosmos is infinite, then the observable portion is only a tiny bubble within a boundless expanse, and yet that bubble is enormous. Its radius, in terms of proper distance today, is about 46.5 billion light-years. Everything we see in the night sky, every galaxy and quasar, lies within this spherical shell. As time marches on, photons from ever more distant regions will reach us. So the observable universe is not static. It is a moving target. There is another cosmic boundary imprinted in the glow of the cosmic microwave background. During the first few 100,000 years after the Big Bang, the universe was a hot plasma in which photons could not travel freely because they scattered off charged particles. Only when the plasma cooled and atoms formed did the cosmos become transparent, allowing radiation to stream unimpeded. The relic radiation from that last scattering surface bathes us today as a microwave whisper, and it is the oldest light we can detect. To understand horizons, it is helpful to think in terms of light cones. Every event in spacetime has a past light cone consisting of all places that could have sent signals to that event, and a future light cone comprising all places it can influence. The expanding universe introduces additional subtleties. There is a Hubble sphere, whose radius is about 14 billion light-years, beyond which galaxies recede faster than light due to expansion. Yet, because the expansion rate changes over time, some light from beyond the Hubble sphere can still reach us. But there is also an event horizon, beyond which even signals emitted now will never arrive. The Hubble sphere is defined by the distance at which recession velocity equals the speed of light. But the event horizon depends on the future evolution of the expansion. If the expansion continues to accelerate, there will be regions of space from which light emitted today will never reach us, no matter how long we wait. This horizon is larger than the Hubble sphere, because the Hubble parameter is decreasing with time. The existence of these horizons reminds us that cosmic edges are dynamic and depend on both past and future expansion histories. Because our horizon is set by time, not by space, the term observable really refers to what we can see now. As the universe ages, photons from more distant regions cross our past light cone, so the observable universe grows. However, if dark energy continues to drive accelerated expansion, the event horizon imposes a permanent limit on the regions we can ever influence or observe. Thus, the edge of the observable universe is both expanding and, in a deeper sense, bounded. Every observer in the universe has their own horizon, because each occupies a unique point in space-time. Two observers separated by billions of light-years would see mostly the same cosmic microwave background, but would inhabit different observable spheres, like islands whose shores slowly recede as their cosmic seas swell. There is no physical barrier at the horizon. Galaxies and light cross it freely, but we cannot witness anything that has not yet emitted light reaching us. In this way, the edge of the observable universe is a concept about information, not about matter. The shape of the horizon is spherical around any given observer, because light travels outward at the same speed in all directions. Yet on the grandest scales, the universe might be infinite, curved like a saddle, or close on itself in a hypersphere. No matter its global geometry, the combination of light speed and cosmic age carves out a finite bubble of the cosmos for each observer. Far from being a literal wall, the edge is like the misty boundary of a dream, shifting as time flows onward. Nothing marks the boundary of the observable universe in space. There is no change in density, no drop in temperature, and no glowing shell at 46 billion light-years. The boundary is a demarcation in time. Beyond it, the universe was too young when the light we see was emitted. It is only by understanding this temporal nature of horizons that one appreciates why the cosmos can be unbounded, yet our view limited. Contemplating this edge invites reflection on time itself. When we peer deeper into space, we are looking further back in time. The cosmic edge is therefore a boundary between present and past, between the now of our existence and the ancient photons that have travelled for aeons. Moving from this concept of spatial edges to temporal depth prepares us to consider light as a time machine. In the chapters to follow, we will use the cosmos itself as a telescope into time. We will see how the universe's expansion stretches the wavelengths of distant light, how astronomers measure distances across vast scales, and how maps of the sky reveal patterns imprinted when the universe was young. We will also explore how the cosmos is expanding in slow motion, and how limitations in brightness and instrumentation challenge our quest. Our journey from edge to depth is a voyage through both space and time. The notion that our universe could be infinite, while our view of it is finite, may feel counterintuitive. Yet this distinction is central to modern cosmology and to our sense of place. A finite, observable sphere within an unbounded cosmos evokes a sense of humility and wonder. We are small, yet connected to a vast, dynamic universe. Understanding horizons sets the stage for seeing how space and time intertwine on cosmic scales. Gravity and expansion play complementary roles in shaping horizons. In the early universe, the dominant density of matter and radiation slowed the expansion, causing the horizon to grow slowly. As the universe aged and dark energy came to dominate, the expansion accelerated and the event horizon emerged. Thus, the edge of the observable universe is not fixed by geometry alone, but by the interplay of the universe's constituents and its expansion history. When cosmologists speak of the scale of the universe, they often refer to comoving distances, which factor out the expansion to provide a coordinate grid on which galaxies remain fixed. Comoving coordinates expand with the universe, making it easier to describe the geometry and to calculate horizons. Proper distance, by contrast, measures the actual separation at a given cosmic time and is therefore larger today than when the light was emitted. Understanding these distinctions helps us make sense of edges and look back times. The cosmic edge is sometimes visualized as a series of nested spheres. Within lies the galaxy, the local group, the Virgo supercluster, and the cosmic web, all contained inside a larger bubble of the observable universe. Beyond that bubble, there may be infinitely many other structures, but they are beyond our reach. The edges of these spheres are conceptual rather than physical, and their radii grow as time progresses. In this sense, the edge is a moving frontier rather than a wall. These considerations lead naturally to the idea that looking far in space is equivalent to looking far in time. Since the finite speed of light means we can only see objects as they were when the light was emitted. The universe itself becomes a time machine. The cosmic horizon marks the earliest time we can see. But within that sphere, we see the universe at many different stages of its history. Our next step is to consider how astronomers use this relationship between distance and time to reconstruct the universe's past. When we observe a nearby star, we are seeing it as it was a few years ago. When we observe a distant galaxy, we see it as it was billions of years ago. This simple fact transforms telescopes into instruments that peer backward in time. Each photon that enters our eye or detector has carried with it a record of the universe's state at the moment of its departure. By comparing photons of different colors and energies, we can decode that history and build a timeline of cosmic events. Redshift is the key to translating light into time. As the universe expands, the wavelengths of photons traveling through space are stretched, moving them toward the red end of the spectrum. Astronomers measure this redshift, denoted by the dimensionless parameter z, by comparing the observed wavelengths of spectral lines to their laboratory values. A larger redshift corresponds to a longer look-back time, because the light has been stretched over a longer cosmic journey. Unlike everyday Doppler shifts caused by objects moving through space, cosmological redshift arises from the expansion of space itself. Galaxies are largely at rest in comoving coordinates. It is space between them that grows, stretching the light traveling through it. Thus, redshift encodes the history of cosmic expansion rather than peculiar velocities. We use redshift as a proxy for distance, but because the universe expanded while the light was in transit, the actual distance to a galaxy now is not simply the light travel time multiplied by the speed of light. For example, one of the most distant galaxies known, catalogued as UDFY-381355539, has a measured redshift of 8.6. Its light left the galaxy when the universe was only about 600 million years old, roughly 4% of its current age. During the 13 billion years since then, the cosmos has expanded dramatically. So although the galaxy emitted its light when it was perhaps 13 billion light-years away, in terms of light travel distance, it is now about 30 billion light-years away in proper distance. Such examples illustrate how redshift and look-back time must be interpreted within an expanding universe. Cosmic time dilation adds another layer to the story. Because the expansion stretches not only the wavelength of light, but also the time intervals between successive wave crests, events observed at high redshift appear to unfold more slowly. A supernova occurring at a redshift of 1 will have its light curve stretched by a factor of 2, so that a 2-week rise and decline in its own frame appears to last a month to us. At a redshift of 10, time dilation would make events appear 11 times longer. This effect, predicted by relativity, has been confirmed by observations of distant supernovae and serves as another tool for understanding cosmic expansion. By analyzing redshifts and time dilations, astronomers construct the cosmic timeline. They can determine when galaxies formed, when stars first lit up, and how quickly structures grew. They also learn how the expansion rate has changed over time, because the relationship between redshift and look-back time depends on the density of matter, radiation, and dark energy. In this way, measuring redshift is akin to reading the universe's diary. When we look at the cosmic microwave background, we are observing radiation that has traveled for over 13 billion years, from a time when the universe was just 380,000 years old. This primordial light reveals a universe filled with sound waves rippling through plasma, patterns that would seed the galaxies and clusters we see today. The redshift of the cosmic microwave background is about 1,100, meaning its wavelengths have been stretched by a factor of 1,000 since emission. Translating redshift into time for such extreme values requires precise models of the universe's expansion history. At more modest redshifts, redshift surveys catalogue millions of galaxies, each with a measured redshift and position on the sky. These surveys allow us to map the three-dimensional distribution of matter and trace how structures have evolved. By comparing the observed distribution at different redshifts, astronomers can test models of galaxy formation and the influence of dark matter and dark energy. In this sense, redshift serves not only as a measure of distance and time, but also as a marker of cosmic evolution. Spectroscopic measurements of redshift rely on atomic fingerprints, absorption or emission lines from hydrogen, helium, and heavier elements. By measuring how far these lines are shifted relative to their known wavelengths, astronomers compute Z with remarkable precision. Photometric redshift techniques estimate redshift using broadband colors and are less precise, but can be applied to billions of galaxies. Both methods translate the observed universe into a cosmic timeline. The concept of look-back time also clarifies why seeing far back does not mean seeing far away in terms of present distance. Because the universe expands while light travels, a galaxy we observe at a look-back time of 10 billion years may now be much farther than 10 billion light years. Conversely, some galaxies we see today at modest redshift may currently be receding faster than light in proper terms, yet their light still reaches us because it was emitted when they were closer. Such counterintuitive facts arise naturally in the framework of general relativity. Redshift and look-back time interweave space, time, and expansion into a tapestry that astronomers continue to unravel. Each measurement carries uncertainties, and converting redshift to age requires assumptions about cosmic parameters. Nonetheless, the accumulation of redshift data over the past century has transformed our understanding of the universe's history. As we move forward, we will see how distances are measured using a ladder of techniques that build upon these observations. Measuring cosmic distances requires more than one tool, because no single method spans the range from nearby stars to distant galaxies. Instead, astronomers use a cosmic distance ladder, in which each rung calibrates the next. The ladder begins with radar measurements within the solar system and trigonometric parallax for nearby stars, extends through variable stars and clusters for nearby galaxies, and reaches out with supernovae, baryon acoustic oscillations, and gravitational waves for the farthest reaches. Each step is built on physical understanding and careful calibration. Trigonometric parallax exploits the Earth's orbit around the Sun. As Earth moves from one side of its orbit to the other, nearby stars appear to shift against the background of distant stars. This tiny angular shift is measured in arcseconds. The largest parallax is less than 1 arcsecond for Alpha Centauri, our closest stellar neighbour. Parallax measurements can reliably measure distances out to a few thousand light-years, providing the foundation for the first rungs of the distance ladder. Space missions such as Hipparcos and Gaia have increased parallax precision dramatically. Beyond parallax, astronomers turn to star clusters and the Hertzsprung-Russell diagram. Open clusters contain stars of similar age and composition at nearly the same distance. By comparing their observed brightness to models, astronomers determine cluster distances and calibrate the brightness of variable stars within them. This step allows the ladder to reach beyond parallax limits and into the domain of nearby galaxies. Main sequence fitting and moving cluster methods further refine the calibration. The ladder's next important rung comes from pulsating stars, known as Cepheid variables. In the early 20th century, Henrietta Swan Leavitt discovered a tight correlation between the period of a Cepheide's pulsation and its intrinsic luminosity. Longer periods correspond to brighter stars. Once the relation is calibrated using parallax, the period of a Cepheid in a nearby galaxy immediately yields its distance. Cepheids can be observed across tens of millions of light-years, making them indispensable for measuring distances to galaxies in the local universe. Different classes of variable stars, such as R Lyrae, complement Cepheids at different luminosities. Together, these variables form a network of standard candles that extend the ladder step by step. Observing them requires careful monitoring, because their brightness changes over days to months. Modern surveys with space and ground-based telescopes have catalogued thousands of these stars, solidifying the ladder's intermediate rungs. Each rung must be robust, because errors propagate upward. At greater distances, the brightness of individual stars becomes too faint to measure, and astronomers turn to explosive events. Type Ia supernovae. These supernovae occur when a white dwarf in a binary system accretes mass from its companion and reaches the Chandrasekhar limit, triggering a thermonuclear explosion. Because the mass at which the explosion occurs is nearly the same in all cases, Type Ia supernovae have a remarkably uniform intrinsic luminosity. They are bright enough to be seen across billions of light-years and serve as standard candles for cosmological distances. By comparing the observed brightness of a Type Ia supernova with its known intrinsic brightness, astronomers determine its distance. When the distances are plotted against redshift, the points trace how the universe's expansion has changed over time. In the late 1990s, two independent teams found that distant Type Ia supernovae were dimmer than predicted by a decelerating universe, implying they were farther away than expected. The conclusion was profound. The expansion of the universe is accelerating, driven by a mysterious form of energy dubbed dark energy. This discovery reshaped cosmology and earned a Nobel Prize. Another rung in the distance ladder comes from sound waves in the early universe. Before recombination, photons and baryons were tightly coupled, and density fluctuations propagated as acoustic waves. When the universe became transparent, these waves froze, leaving behind spherical shells of higher density. The distance that sound could travel in that early plasma defines a standard ruler, baryon acoustic oscillations, which today spans about 490 million light-years. By measuring the statistical excess of galaxy pairs separated by this scale, astronomers determine cosmic distances and expansion history. Detecting BAO involves measuring the spatial distribution of millions of galaxies over large volumes of the universe. The subtle peak in the galaxy correlation function, corresponding to the sound horizon, provides a powerful constraint on cosmological parameters. Combined with measurements of the cosmic microwave background and supernovae, BAO helps pin down the density of matter and the influence of dark energy. Unlike standard candles, BAO acts as a standard ruler, complementing the ladder with a geometric measurement. It demonstrates how primordial physics echoes across cosmic time. Gravitational waves add a new rung to the ladder. When two massive objects, such as neutron stars or black holes, spiral toward each other, they radiate gravitational waves that carry away energy. The waveform of this radiation encodes the masses of the objects, and thus the total energy emitted. By comparing the observed amplitude and frequency evolution, the chirp, to theoretical models, astronomers infer the luminosity distance directly, without calibration. Such sources are called standard sirens. To convert a standard siren distance into a measurement of cosmic expansion, one must also know the source's redshift. In 2017, The gravitational wave event, GW170817, was accompanied by a gamma-ray burst and an optical counterpart, allowing astronomers to measure both its distance and redshift. The resulting estimate of the Hubble constant was about 70 kilometers per second per megaparsec, with large uncertainties because only one event was available. As more standard sirens are detected, they will provide an independent test of the cosmic distance scale and may help resolve tensions between different measurements. Taken together, these methods form a ladder reaching from our solar neighborhood to the edge of the observable universe. Each rung relies on the one below for calibration, and cross-checks between different methods ensure robustness. The cosmic distance ladder is a testament to human ingenuity, combining geometry, stellar astrophysics, explosive transients, primordial physics, and gravitational waves into a coherent picture. Without it, our understanding of the size, age, and expansion of the universe would be far more uncertain. Behind every rung lies deep physics. Parallax relies on the geometry of Earth's orbit. Variable stars on pulsation driven by opacity changes. Supernovae on quantum mechanics of degenerate matter. BAO on sound propagation in a plasma. And gravitational waves on general relativity. The ladder is not just a set of empirical tricks. It is a synthesis of many branches of physics. Each rung is a story of discovery and refinement, from Leavitt's work with photographic plates to modern detectors of gravitational waves. These stories reveal how we have come to measure distances that once seemed unfathomable. The sound horizon, imprinted by baryon acoustic oscillations, is a relic of an epoch when the universe was only a few 100,000 years old. Acoustic waves created concentric shells around primordial overdensities, similar to ripples from a stone dropped in a pond. After recombination, photons streamed freely, and the baryonic shells remained, slightly overdense relative to their surroundings. Billions of years later, these shells influence where galaxies form, leaving a statistical imprint detectable in galaxy surveys. Through BAO, we probe both the early universe and cosmic expansion. The gravitational wave distance scale is still in its infancy, but its potential is enormous. Unlike electromagnetic observations, gravitational waves are unaffected by dust or intervening matter, providing a clear measure of distance. Standard sirens could eventually deliver precise constraints on the Hubble constant and the equation of state of dark energy. Future detectors will observe mergers at greater distances and in greater numbers, offering a new perspective on cosmic expansion. With these tools, we continue to refine our cosmic map. Just as distances require a ladder, mapping the sky requires a coordinate system. Since antiquity, astronomers have imagined the heavens as a vast sphere surrounding Earth. On this celestial sphere, they mark positions using a system akin to Earth's latitude and longitude, right ascension and declination. Right ascension measures the angular distance eastward from a reference point on the celestial equator, while declination measures the angle north or south of that equator. Unlike terrestrial longitude, right ascension is not measured in degrees, but in hours. There are 24 hours in a full circle, so 1 hour of right ascension corresponds to 15 degrees. Each hour is subdivided into minutes and seconds, just as time is. This system reflects the daily rotation of Earth, linking the sky's coordinates to the passage of time. Declination, by contrast, is measured in degrees, arc minutes, and arc seconds from the celestial equator up to the poles. These coordinates allow astronomers to catalogue and navigate the sky. When a telescope is programmed to observe an object at, say, 12 hours of right ascension and 30 degrees of declination, it knows exactly where to point. Star charts, planetarium software, and professional databases all rely on this celestial coordinate system. Without such a standardized grid, the task of mapping and sharing observations of the heavens would be chaotic. The system is flexible enough to account for precession and nutation over centuries. All sky surveys aim to catalogue celestial objects across the entire sphere. Modern surveys use robotic telescopes that repeatedly scan the sky, capturing images in multiple wavelength bands. Because a telescope's field of view covers only a small patch of sky, surveys must combine many pointings. Each pointing overlaps with its neighbours so that the final mosaic maintains nearly uniform sensitivity. This process of combining multiple exposures is called mosaicing. There are two main approaches to mosaicing. In a discrete mosaic, each field is observed separately and later stitched together by aligning stars and correcting for differences in sensitivity. An alternative is on-the-fly mapping, in which the telescope scans continuously across the sky, taking data while moving. The resulting image is reconstructed using specialized algorithms. Each method has advantages. Discrete mosaics offer precise control over exposure time, while on-the-fly mapping can cover large areas more efficiently. Astronomers choose based on the survey's goals. Creating seamless mosaics requires careful calibration. Differences in atmospheric conditions, detector sensitivity, and sky background between exposures must be corrected. Overlapping regions are used to match photometric 0 points and adjust for any residual distortions. The resulting images are then projected onto a standard coordinate grid and combined. The final product is a map of the sky with uniform depth and resolution, revealing patterns across vast areas. Every survey faces selection effects. A flux-limited survey, which observes all objects brighter than a certain magnitude, will naturally detect only the most luminous objects at great distances. This leads to the Malmquist bias. The average luminosity of objects in the sample increases with distance, because fainter objects fall below the detection threshold. Surface brightness and compactness limits further bias samples, causing diffuse or low surface brightness galaxies to be underrepresented. Without correcting for these effects, conclusions about galaxy populations and evolution could be misleading. To account for selection effects, astronomers define a selection function. The selection function quantifies the fraction of objects observed relative to the intrinsic population as a function of position on the sky, magnitude, color, or distance. Knowing the selection function allows researchers to weight their samples appropriately, correcting for missing objects and biases. Surveys such as the Sloan Digital Sky Survey implement complex algorithms to select targets, balancing random sampling with specific science goals. Understanding the selection function is critical when interpreting survey results. Some surveys deliberately target specific populations, such as red giant stars in the Milky Way, and thus oversample certain types of objects. Others are purely random within magnitude bins, like the main red star sample described in SDSS documentation. In either case, the selection function must be well characterized to ensure that statistical analyses, whether of stellar kinematics or cosmological parameters, remain unbiased. As surveys grow in size and complexity, modeling selection effects becomes an increasingly sophisticated endeavor. Mapping the sky also means dealing with our position inside the Milky Way. Dust lanes obscure much of the galactic plane, creating a zone of avoidance where optical surveys cannot see beyond. Infrared and radio wavelengths penetrate dust better, so surveys like the 2-micron all-sky survey and HI surveys help fill in gaps. combining data across wavelengths provides a more complete picture of the sky. Nevertheless, selection effects due to extinction and crowding remain challenges. Despite these obstacles, sky maps have revealed the cosmic web, a network of filaments and voids formed by the gravitational growth of primordial fluctuations. Clusters of galaxies mark nodes where filaments intersect, while vast empty regions span tens of millions of light-years. By comparing maps at different redshifts, astronomers see how this cosmic web evolved. Patterns such as baryon acoustic oscillations imprinted in the distribution of galaxies become visible, linking maps to the physics of the early universe. Our mapping of the sky owes much to the coordinate system of right ascension and declination, and to the advances in imaging and data processing. As telescopes survey deeper and with finer resolution, maps will become ever more detailed, revealing smaller galaxies and faint structures. At the same time, modeling selection effects and calibrating mosaics will remain essential. The sky is both map and laboratory, a canvas on which the history of the universe is painted. Our exploration of the sky leads naturally to questions about why galaxies appear to move away from us. The answer lies in the expansion of space described by the Hubble-Lemaitre law. In the late 1920s, observations of galaxies' redshifts and distances revealed a linear relationship. The recessional velocity of a galaxy is proportional to its distance from us, expressed as v equals h0d. This relationship indicates that space itself is expanding, carrying galaxies along. The proportionality constant h0 is called the Hubble constant. Its value is currently measured to be around 70 kilometers per second per megaparsec, meaning that a galaxy a megaparsec away recedes at 70 kilometers per second. The exact value is the subject of active research because different methods yield slightly different results. The reciprocal of the Hubble constant provides the Hubble time, an estimate of the universe's age if the expansion had always been at its current rate. Today, the Hubble time is roughly 14 billion years. However, the Hubble parameter is not truly constant. It changes over cosmic time as the densities of matter, radiation, and dark energy evolve. Early in the universe, radiation dominated and the expansion was rapid. Later, matter dominated and expansion slowed. Recently, dark energy has taken over, causing acceleration. The scale factor A of t describes how the size of the universe changes relative to today, linking the Hubble parameter to the rate of change of A. Understanding this evolution is central to cosmology. On human timescales, cosmic expansion is imperceptible. The Milky Way is bound by gravity and does not expand. And even within galaxy clusters, the gravitational binding overwhelms expansion. But on scales of tens or hundreds of millions of light-years, expansion dominates. Over billions of years, distances between galaxy clusters double, triple, and more. This slow motion of expansion shapes the history of the universe and our understanding of its fate. In the early universe, the gravitational attraction of matter and radiation slowed the expansion. But as space expanded, the density of matter diluted. Eventually, dark energy, whose density remains roughly constant as the universe expands, became significant and began to dominate. Observations of distant type Ia supernovae in the 1990s showed that the expansion is not decelerating, as expected, but accelerating. This finding was surprising, because gravity from matter should slow expansion, not speed it up. The implication is that some form of energy with negative pressure pervades space. Dark energy, as this unknown component is called, is thought to make up about 68 to 70% of the total energy density of the universe. Ordinary matter, including stars, planets, gas, and dust, accounts for only about 5%, with the rest being dark matter. Despite being the dominant component, dark energy is not directly detected. Its existence is inferred from its gravitational effects. Whether it is a cosmological constant, a property of space itself, or something more exotic, remains one of the biggest open questions in physics. The discovery of cosmic acceleration earned 3 physicists the Nobel Prize in 2011. Using Type Ia supernovae as standard candles, the teams measured distances and redshifts and found that distant supernovae were fainter than expected. This meant they were farther away than predicted by a decelerating universe, indicating that expansion had sped up. The results were cross-checked with baryon acoustic oscillations and the cosmic microwave background, forming a consistent picture. Yet the physical nature of dark energy remains elusive. Cosmologists describe dark energy's effect through an equation of state parameter, W, which relates its pressure to its density. If dark energy is a cosmological constant, then W equals -1. Measurements of supernovae, BAO, and the CMB currently suggest W is close to -1, but small deviations could indicate more complex physics. Future surveys aim to measure W more precisely by observing thousands of supernovae and mapping BAO at multiple redshifts. In this way, cosmic expansion becomes a laboratory for fundamental physics. The energy budget of the universe summarizes its composition. Ordinary baryonic matter, the stuff of stars, planets, and people, constitutes only a small fraction. Dark matter, composed of unknown particles, makes up about 27% and provides the gravitational scaffolding for galaxy formation. Dark energy fills the rest, driving accelerated expansion. Radiation, once dominant in the hot early universe, now contributes negligibly. These proportions are measured with high precision by observations of the cosmic microwave background, supernovae, and large-scale structure. Cosmic acceleration has profound implications for the ultimate fate of the universe. If dark energy remains constant, the expansion will continue to accelerate, causing galaxies outside our local group to recede ever faster. Eventually, only the nearest galaxies will remain visible, and the cosmic microwave background will fade. If dark energy's density increases over time, a big rip could eventually tear apart galaxies, stars, and atoms. Conversely, if dark energy decays, the universe could slow and recollapse. Observations over the coming decades may shed light on these possibilities. One puzzle in modern cosmology is the so-called Hubble tension. Measurements of the Hubble constant using the cosmic distance ladder, parallax, Cepheids, and Type Ia supernovae yield a value around 73 kilometers per second per megaparsec. Measurements based on the cosmic microwave background and early universe physics yield a lower value around 67. The difference exceeds known uncertainties and may point to new physics or unrecognized systematics. Standard sirens from gravitational waves offer a potential independent path to resolve this tension. The first standard siren measurement from GW170817 gave a Hubble constant of about 70 kilometers per second per megaparsec, albeit with large error bars. With more events, the uncertainty will shrink, providing a valuable cross-check. This interplay between different methods exemplifies the scientific process. Independent measurements build confidence and sometimes reveal discrepancies that lead to deeper understanding. The expansion of the universe, once discovered through the motion of nebulae, remains a fertile field of inquiry. Dark energy ensures that mystery endures. In our final section, we consider the practical limits of observation. The expansion of the universe not only stretches wavelengths, but also dims the apparent brightness of distant objects. For extended objects like galaxies, the surface brightness, the amount of light per unit area, decreases steeply with redshift as 1 plus z to the power of -4. This Tolman dimming arises because photons lose energy, arrive less frequently due to time dilation, and the apparent area increases as the universe expands. Together, these effects make high redshift galaxies difficult to detect. At a redshift of 1, Tolman dimming reduces surface brightness by a factor of 16. At redshift 10, the factor is over 11,000. Even if a galaxy's total luminosity remains the same, its light is spread over a larger apparent area and reduced in energy, challenging our telescopes. To detect such faint signals, astronomers require long exposure times, large collecting areas, and sophisticated data processing. These demands drive the design of instruments like the James Webb Space Telescope and future observatories. Correcting observations for redshift also requires K corrections. Because a galaxy's light is stretched, the wavelength band recorded by a telescope corresponds to a bluer band in the galaxy's rest frame. The K correction adjusts the observed magnitude to what it would be if measured in the same band at 0 redshift. This correction depends on the source's spectrum and the filter used, and it is distinct from cosmological dimming. It is purely an instrumental effect. Accurate K corrections are essential when comparing galaxies at different redshifts. Time dilation also affects our ability to detect transient events. A supernova at redshift 2 will appear to rise and fade over twice the time it would in its own rest frame. While this stretching can aid detection by lengthening the event, it also requires longer monitoring to capture the full light curve. At very high redshifts, time dilation means that events which last days in their own frame may stretch to months or years in hours. This complicates survey design and requires patience in data analysis. Detection limits are set not only by the intrinsic brightness of sources, but also by the noise in our instruments and the sky background. In practice, astronomers define a detection threshold in terms of the signal-to-noise ratio, often requiring a detection to exceed the background by a factor of 2 or more to claim significance. The surface brightness limit of an image is the brightness at which extended objects can be distinguished from fluctuations in the background. Telescopes with larger apertures collect more photons, improving sensitivity, but sky brightness, detector noise, and atmospheric conditions impose limits. Space telescopes eliminate atmospheric noise, but are constrained by instrument lifetime and cost. Despite these challenges, new technologies continually push the frontier. Advanced CCDS and infrared detectors reduce noise, while adaptive optics and space-based platforms mitigate atmospheric effects. Interferometers combine light from multiple telescopes to achieve higher resolution. Gravitational wave detectors observe ripples in spacetime rather than photons, opening a new window entirely. Each advancement extends our reach, allowing us to see fainter, farther, and in different messengers, enriching our view of the cosmos. As we reach the end of this first part of our journey, we reflect on the path traveled. We began at the mysterious edge of the observable universe, defined not by a wall, but by time and the speed of light. We then used redshift as a clock to peer backward and learned how distance measurements build upon one another. We mapped the sky with careful coordinates, mosaics, and awareness of selection effects, and we considered how expansion, dark energy, and acceleration shape our fate. Finally, we confronted the limits imposed by cosmic dimming, time dilation, and detection thresholds. The story of the universe is not confined to these chapters. Beyond the horizon lie regions we will never see, and ahead of us lie new tools and discoveries. In the next part, we will delve deeper into the birth of stars and galaxies, the formation of large-scale structure, and the interplay of matter, radiation, and gravity. The journey continues, and the cosmos invites us onward with quiet wonder and an ever-expanding horizon. As our journey continues, we leave behind the notions of cosmic boundaries and wander into a domain where the universe's own light carries whispers from the beginning. The story picks up just as the last part eased into the idea that the cosmos is bathed in an afterglow. Now we gently drift closer to that glow, describing it without hurry, noticing how it wraps us in the warmth of information and the chill of ancient photons. We recall that the universe once shimmered as a hot plasma, dense and opaque, and then gradually became transparent when protons and electrons combined to form neutral hydrogen, releasing the radiation that now permeates the sky. That moment became a cosmic freeze frame, capturing patterns of density and temperature that would later blossom into galaxies and clusters. This afterglow is not uniform. Its subtle ripples guide us like soft waves, hinting at the seeds of all structure. In the epoch before this transformation, matter and light were intimately intertwined. The early cosmos was like a fog of charged particles and photons, scattering and rescattering light so thoroughly that no photon could travel far. The universe expanded and cooled over hundreds of thousands of years. And finally, those interactions slowed enough for electrons to bind to protons, creating neutral atoms and allowing photons to stream freely. These photons have been traveling ever since, stretching their wavelengths as space has grown, and now they fill the microwave band at a temperature of around 2.725 Kelvin. This is the cosmic microwave background, a near-perfect blackbody radiation field, the most pristine relic we have from the infancy of everything we know. Its temperature differences are minute, only 1 part in 100,000, but those differences reveal an astonishing amount about the cosmos. Imagine standing on a hill at night and looking across a landscape in the early morning mist. The faint variations in the mist's density hint at valleys and mountains you cannot yet see. In a similar way, the small temperature fluctuations in the microwave background map the tiny density variations present in the primordial plasma. Gravity amplifies these variations over cosmic time, turning gentle ripples into cosmic structures. When you trace your mind back to that early time, the fog lifts slowly, the universe calms, and atoms form. Light is allowed to travel and carry information to us across billions of years. The recombination process left behind the cosmic microwave background, our window onto the state of the universe when it was just 380,000 years old. During this recombination era, electrons paired with protons to form neutral hydrogen, and in doing so, they ceased to scatter photons efficiently. This process is sometimes called the surface of last scattering, though the term is slightly misleading, as it was not a sharp surface, but rather a relatively brief period when photons decoupled from matter. The imprint of this era is what we observe today as the CMB. The universe at that time was about 2,700 degrees Celsius, yet these photons have cooled by the expansion of space to a few Kelvin. They now form an almost uniform background that we can detect in every direction. The nearly uniform glow allows us to measure the geometry of space, because slight temperature differences reflect how angles are projected over cosmic distances. The physics behind the CMB's spectrum is simple yet profound. A blackbody spectrum depends only on temperature. Therefore, measuring the spectrum of the CMB reveals its average temperature. Observations have confirmed that this background radiation is indeed an almost perfect blackbody, with any deviations being extremely small. Such a perfect spectrum argues strongly for a cosmic origin rather than one tied to our solar system or our galaxy. Early debates about whether the microwave background could be produced by dust within the Milky Way or by distant radio sources were settled when the spectral measurements matched a blackbody curve. The isotropy of the CMB across the sky further confirmed that this light is not from a local source, but permeates the universe. While the overall temperature is nearly uniform, the anisotropies, the tiny deviations, carry essential information. These temperature differences correspond to slightly denser or less dense regions in the primordial plasma. In regions of slight overdensity, gravity would try to compress the matter, heating the plasma. In underdense regions, the plasma would be rarefied and cooler. These variations set the stage for the cosmic structures that formed later. It is remarkable that the seeds of galaxies, clusters, and large-scale filaments were already present as small ripples less than 1 part in 10,000 in the early universe. Without these fluctuations, matter would have remained homogeneous, and there would be no structure to speak of. The interplay between gravity and pressure created acoustic oscillations in the photon baryon fluid before recombination. Imagine a cosmic drum where gravity acts like a drumhead being pulled inward, and radiation pressure pushes back. The competition between these forces set up sound waves that propagated through the plasma. When the universe became transparent, these oscillations froze in place, imprinting characteristic scales on the CMB that we now observe as acoustic peaks in the angular power spectrum. Each peak corresponds to modes that had undergone a specific number of compressions or rarefactions. The first peak represents a compression mode reaching maximum amplitude at decoupling. The higher peaks represent additional half oscillations, creating a pattern that depends sensitively on the density of baryons, dark matter, and the curvature of space. The location of the first acoustic peak tells us about the geometry of the universe. In a flat universe, the angle subtended by the sound horizon, the largest distance sound could have travelled by recombination, appears about 1 degree on the sky. If space were positively curved, this angle would appear larger. If negatively curved, it would appear smaller. Measurements of the CMB anisotropies have found the first peak near the scale predicted for a flat geometry, indicating that the universe is very close to spatially flat. The ratios of subsequent peak heights reveal the baryon density relative to dark matter. A higher baryon content enhances compressional peaks relative to rarefaction troughs. In this way, the CMB acts as a cosmic forensic tool, allowing us to infer the composition of the universe long before stars or galaxies formed. When we examine the CMB anisotropy spectrum, we see a series of peaks and troughs. These features are sometimes called the acoustic peaks because they arise from sound waves in the early plasma. The amplitude and spacing of these peaks contain information about the physical conditions in the early universe. For example, the location of the first peak reflects the scale of the sound horizon at decoupling, which in turn depends on the expansion history. The relative heights of the peaks are influenced by the ratio of baryons to photons and by the presence of dark matter. Through careful analysis, cosmologists can infer these ratios and thus determine the relative contributions of normal matter and dark matter to the total energy density. Another aspect of the CMB that offers insight is its polarization. Polarization arises when anisotropic radiation scatters off free electrons. In the early universe, before recombination, the radiation field around each electron was nearly isotropic, producing little net polarization. However, by the time of decoupling, small anisotropies had grown, and Thomson's scattering of this anisotropic radiation generated polarized light. The polarization pattern can be decomposed into two types: E modes and B modes. E modes have a divergence-like pattern with no handedness, while B modes exhibit a curl component and can have handedness. Scalar perturbations in the density field produce only E modes, whereas tensor perturbations, such as gravitational waves from inflation, can produce both E and B modes. Polarization is weaker than temperature anisotropies, but it provides additional constraints. The E mode spectrum has its own acoustic peaks, shifted in phase relative to the temperature peaks because of the different response of polarization to the oscillations in the plasma. The cross-correlation between temperature and E-mode polarization, known as the TE spectrum, reveals the time of recombination and the physics of reionization. These polarization measurements help break degeneracies between cosmological parameters that would otherwise be inseparable from temperature data alone. They also offer a chance to detect the imprint of primordial gravitational waves, since B modes cannot be produced by density perturbations in the absence of vector or tensor modes. Detecting primordial gravitational waves through B mode polarization is extremely challenging. The amplitude of the signal is expected to be tiny, and there are foreground contaminants. Yet a detection would provide a direct window into the inflationary epoch, a fraction of a second after the Big Bang. A gravitational wave background would polarize the CMB in a curl pattern on large scales, leaving a B-mode signature. Many experiments, both ground-based and space-based, have been built to search for this signal. The BICEP and Keck experiments at the South Pole operate in the calm, dry conditions of Antarctica to reduce atmospheric noise, and they observe at multiple frequencies to isolate the primordial signal from galactic dust. One of the biggest challenges in measuring B modes is the contamination from galactic foregrounds. The Milky Way is filled with dust and magnetic fields. Dust grains align with magnetic fields and emit polarized radiation, particularly at high frequencies, while synchrotron emission from cosmic ray electrons spiraling in magnetic fields dominates at low frequencies. Free emission, produced by electrons scattering off ions in the warm interstellar medium, adds unpolarized contamination. Separating these signals from the primordial CMB requires observations at multiple frequencies and careful modeling of the foregrounds. This is why experiments like Planck, with 9 frequency bands, have been so valuable. In 2014, the BICEP-2 team announced a detection of B-mode polarization at a level that suggested a significant gravitational wave signal. The result caused excitement around the world. However, subsequent analysis, including data from the Planck satellite, revealed that polarized dust emission was more significant than originally estimated. A joint analysis by Planck, BICEP-2, and the Keck array found that the signal was dominated by galactic dust, and after foreground subtraction, only an upper limit on the gravitational wave amplitude could be placed. Thus, the search for primordial B modes continues, with improved instruments and methods designed to further suppress foregrounds. Another phenomenon that modifies the CMB patterns is gravitational lensing. Structures between us and the last scattering surface can deflect the paths of CMB photons by small angles. Typical deflections are only a few arc minutes, but these deflections rearrange the temperature and polarization patterns. Lensing smooths the acoustic peaks in the temperature power spectrum by redistributing power from larger scales to smaller scales. It also generates B-mode polarization by distorting the E mode pattern, creating a secondary source of B modes that must be removed to reveal any primordial signal. The lensing deflection field can itself be reconstructed from the CMB data, allowing us to map the integrated mass distribution along the line of sight. Lensing does more than just add complications, it opens new windows. By measuring the lensing convergence field, cosmologists can reconstruct the projected gravitational potential of the universe and probe the distribution of dark matter. These lensing measurements also allow cross-correlations with galaxy surveys to test models of structure formation and the relation between luminous and dark matter. Furthermore, the lensing signal offers constraints on neutrino masses, as massive neutrinos suppress structure growth on small scales. The combination of CMB lensing and other datasets thus helps piece together the cosmic web and the physics of its evolution. Another secondary effect, imprinted on the CMB, is the integrated Sachs-Wolf effect. This effect arises when CMB photons traverse evolving gravitational potentials. If the potentials change in time, as they do in a universe with dark energy, photons gain or lose energy, leading to temperature shifts on large scales. In a matter-dominated universe with constant gravitational potentials, the effect vanishes. But in our dark energy-dominated universe, the decay of potentials at late times causes a small increase in power at the largest angular scales. Cross-correlation of the large-scale CMB anisotropy with galaxy surveys has provided evidence for this effect, offering an independent probe of dark energy. The Sunyaev-Zeldovich SZ effect is another important secondary imprint. When CMB photons pass through hot gas in galaxy clusters, they can be inverse Compton scattered by energetic electrons. This scattering can boost photon energies, distorting the blackbody spectrum. The thermal SZ effect produces a decrement in intensity at frequencies below around 217 GHz and an increment above, creating a characteristic spectral shape. There is also a kinetic SZ effect, caused by the bulk motion of the gas relative to the cosmic rest frame. The SZ effect is unique in that its magnitude depends primarily on the integrated pressure of the cluster and is nearly independent of redshift, making it a valuable tool for detecting clusters out to great distances. Observations of the SZ effect complement X-ray observations of clusters. X-ray emission traces the square of the electron density and is more sensitive to denser regions, while the SZ effect traces the line of sight pressure. Together, these measurements allow us to estimate cluster masses and derive cosmological parameters. The abundance and distribution of clusters as a function of redshift provide information on the matter density and the amplitude of fluctuations. Experiments like Planck, the Atacama Cosmology Telescope, and the South Pole Telescope have used the SZ effect to construct cluster catalogues and to test cosmological models. The kinetic SZ effect is more difficult to detect because its amplitude is smaller and it lacks the distinctive spectral signature of the thermal effect. But measuring it can reveal the velocity field of clusters and the growth of structure. While the SZ effect and gravitational lensing occur along the line of sight, there are also relic backgrounds from particles that decoupled even earlier than photons. Neutrinos are among these particles. The cosmic neutrino background decoupled about 1 second after the Big Bang, much earlier than recombination, and has been freely streaming ever since. The predicted temperature of the neutrino background today is about 1.95 Kelvin. Although these relic neutrinos are abundant, they interact very weakly and have extremely low energies, making them extremely difficult to detect directly. Instead, Their existence is inferred indirectly from their influence on nucleosynthesis, cosmic expansion, and the CMB anisotropy patterns. The energy density of neutrinos affects the expansion rate in the early universe, which influences Big Bang nucleosynthesis and the pattern of CMB anisotropies. The effective number of neutrino species, often denoted as N sub EFF, quantifies the contribution of relativistic species to the radiation density. In the standard model, with 3 neutrino flavors, N sub EFF is predicted to be slightly more than 3 because of slight heating when electron-positron pairs annihilate. Measurements of the CMB have indeed found values consistent with this prediction, providing strong evidence for the cosmic neutrino background. Direct detection of relic neutrinos is an extraordinary challenge. Their energies correspond to wavelengths on the order of tens of centimeters, and their interactions with matter are exceedingly rare. Proposed detection methods involve capturing relic neutrinos on beta-decaying nuclei. One method uses tritium. Neutrino capture would cause a beta decay with a slightly higher energy electron than the natural decay, allowing it to be distinguished. The Ptolemy experiment aims to use about 100 grams of tritium to detect this capture process, with a demonstration of a smaller mass planned around the middle of the decade. Achieving sufficient energy resolution to separate the neutrino capture signal from the background of natural decay is extremely demanding. The cosmic neutrino background also leaves its imprint through gravitational effects. Massive neutrinos slow the growth of structure on small scales because their free streaming smooths out density perturbations. This effect slightly modifies the power spectrum of matter fluctuations, and consequently, the lensing and anisotropy spectra of the CMB. By combining CMB measurements with observations of galaxy clustering and weak gravitational lensing, cosmologists can place upper limits on the sum of neutrino masses. These limits currently lie below about 0.12 electron volts, demonstrating the sensitivity of cosmological data to neutrino properties. Future surveys aim to reduce these uncertainties further and perhaps achieve a detection of the neutrino mass hierarchy. Another quiet but potentially detectable background is the relic gravitational wave background from inflation. Inflationary theory predicts that quantum fluctuations in spacetime were stretched to cosmic scales, generating gravitational waves that would imprint a distinctive pattern of B-mode polarization in the CMB. The amplitude of this pattern is characterized by the tensor to scalar ratio, often denoted by R. A detection of R would provide direct evidence of inflation and measure the energy scale of this epoch. Current CMB experiments have placed upper limits on R, indicating that the amplitude of primordial gravitational waves is small. Future experiments, including proposed satellite missions, aim to push sensitivity further and perhaps detect this elusive signal. To understand the cosmic microwave background fully, we must also consider the myriad sources of foreground emission. Our galaxy contains cosmic rays, magnetic fields, ionized gas and dust, all of which emit radiation that can contaminate CMB observations. Synchrotron emission arises when high-energy electrons spiral around magnetic field lines. This emission is most intense at low frequencies, typically between 20 and 60 gigahertz, and is often highly polarized. The intensity and spectral index of synchrotron emission vary across the sky, reflecting the distribution of cosmic ray electrons and magnetic field strength. Supernova remnants and radio spurs contribute strongly to the synchrotron foreground. Free emission, or thermal Bremsstrahlung, occurs when free electrons scatter off ions in the interstellar medium. Unlike synchrotron emission, free emission is generally unpolarized and has a fairly flat spectrum over the microwave bands. It becomes important at intermediate frequencies, around 50 to 60 GHz. Because free emission correlates with the distribution of ionized gas, it can be traced by observations of hydrogen and helium emission lines, such as the H-alpha line. Removing free emission from CMB data involves combining these traces with microwave maps to model the emission and subtract it. Thermal dust emission is another major foreground. Interstellar dust grains absorb ultraviolet and visible light from stars and re-emit it in the far infrared and submillimeter bands. This emission becomes significant at frequencies above 100 GHz and peaks around 150 to 200 GHz. Dust grains are not perfect spheres. They tend to align with galactic magnetic fields, leading to polarized emission. The polarization fraction depends on the properties of the dust and the magnetic field geometry. Dust emission is thus a critical contaminant in polarization measurements. Its spectrum can be modeled as a modified blackbody with a temperature around 20 Kelvin and an emissivity index that determines how quickly the intensity falls with frequency. The interstellar medium is not uniform, but consists of hot ionized gas, warm neutral gas, and cold dense clouds. This complex mixture introduces spatial variations in the foregrounds. Hot ionized gas bubbles, created by supernova explosions, release high-energy electrons that emit synchrotron radiation. Cold neutral hydrogen clouds can emit in the 21 centimeter line, which can contaminate low-frequency observations. There are also anomalous microwave emissions, possibly from spinning dust grains. All these components must be carefully modeled and removed to isolate the cosmological signal. Extragalactic foregrounds include emission from radio galaxies, quasars, and the cosmic infrared background, which is produced by distant dusty galaxies. These sources can be point-like at the resolution of CMB instruments, and therefore appear as small spots or slight enhancements in the maps. Extragalactic radio sources often dominate at low frequencies, while the cosmic infrared background becomes significant at higher frequencies. Removing these sources involves cataloging known objects, masking bright sources, and modeling the statistical properties of faint populations. The residual contamination is treated as additional noise in cosmological analyses. Foreground separation relies on exploiting the different spectral and spatial properties of the various signals. Multi-frequency observations are essential. By comparing maps at different frequencies, one can fit for the contributions of synchrotron, free, dust, and the CMB. Techniques like internal linear combination, template fitting, and parametric modeling are used. The success of these methods depends on the accuracy of the foreground models. The Planck mission's 9 frequency bands have greatly improved our ability to separate foregrounds and have produced maps of the CMB with unprecedented precision. Systematic effects in experiments can also mimic or obscure cosmological signals. Instrument calibration errors, beam asymmetries, time-dependent gain variations, and detector noise all have to be characterized and mitigated. Ground-based instruments must account for atmospheric emission and water vapor fluctuations. Space missions avoid many atmospheric problems, but face challenges like temperature fluctuations and cosmic ray hits. Precise control of systematics is essential, especially for polarization measurements where the signal is small compared to the total intensity. Repeated observations, cross-checks with different instruments, and robust data analysis. Pipelines help ensure reliable results. Despite the challenges posed by foregrounds and systematics, the rewards are great. The cosmic microwave background has given us a wealth of information about the composition and evolution of the universe. From the acoustic peaks, we derive that ordinary matter constitutes only about 5% of the total energy density, while dark matter makes up roughly 27%, and the remainder is dark energy. The Hubble constant, which measures the current expansion rate, is about 67 kilometers per second per megaparsec. These numbers come from fitting cosmological models to the CMB data, and they are corroborated by other observations, such as baryon acoustic oscillations and supernova distances. The age of the universe can also be read from the CMB. By measuring the angular scale of the sound horizon and the ratio of matter and radiation densities, cosmologists infer that the universe is about 13.8 billion years old. This result agrees remarkably well with age estimates from the oldest stars and globular clusters. The concordance of these measurements reinforces the reliability of the cosmological model and the CMB as a probe. It is awe-inspiring to realize that a faint glow discovered accidentally in 1965 now provides the most precise clock for cosmic history. The CMB also reveals the seeds of cosmic structure. The pattern of anisotropies reflects the spectrum of primordial fluctuations, which is nearly scale invariant. Small differences in temperature correspond to density contrasts that gravity amplifies over billions of years to form galaxies and clusters. These seeds came from quantum fluctuations stretched during inflation, and their distribution encodes the physics of that epoch. The smoothness of the CMB on large scales suggests that inflation smoothed out any initial irregularities, while the small but non-zero fluctuations indicate the quantum origin of structure. The amplitude and spectral tilt of these fluctuations provide clues to the shape of the inflationary potential. One can think of the CMB as a photograph taken when the universe was very young. It freezes in time a pattern of sound waves and density fluctuations. From this pattern, we can infer not only the content and geometry of the universe, but also test fundamental physics. For example, the CMB data constrain the number of light particle species, the nature of dark matter, and possible deviations from general relativity. It provides a laboratory for high-energy physics at energies far beyond what can be achieved on Earth. The fact that we can glean such information from faint microwaves is a testament to the power of careful measurement and theoretical insight. The nearly perfect uniformity of the CMB was once considered a puzzle. How could regions of the universe separated by distances too great for light to have traveled between them have nearly the same temperature? Inflation provides a natural solution. A brief period of exponential expansion smoothed out any temperature differences and placed regions that were once in causal contact far apart. This theory also predicts the nearly scale-invariant spectrum of perturbations and the possible presence of primordial gravitational waves. In this way, the CMB sits at the intersection of cosmology and particle physics, linking the largest scales with the smallest. Although the overall picture is consistent, there are intriguing anomalies and puzzles. For example, the CMB exhibits a large cold spot, a region of the sky where the temperature is slightly lower than average over a relatively large area. There are also hints of hemispherical asymmetry and alignments of multipoles. These features might be statistical flukes, but they have provoked discussions about possible departures from the simplest cosmological models. Whether they represent new physics or simply the expected variance of random fields, remains an open question. Future CMB missions may help resolve these mysteries. Looking ahead, several new experiments are planned to probe the CMB more deeply. Ground-based observatories with many more detectors aim to map the sky at high resolution and sensitivity. Space missions under consideration would provide all sky polarization measurements, free from atmospheric interference. These efforts hope to measure the tensor-to-scalar ratio to unprecedented precision, potentially detecting the B-mode signal of inflation. They also aim to refine our understanding of neutrino properties, dark energy, and the sum of neutrino masses. Each incremental improvement in measurement opens the possibility of new discoveries. As we continue our exploration of the afterglow, we marvel at the richness of information contained in a nearly featureless field of microwaves. The cosmic microwave background is a cosmic whisper, a relic from a time before stars, galaxies, or planets. By listening carefully to that whisper, we learn about the composition, geometry, age, and early dynamics of the universe. We are reminded that even in the smallest temperature fluctuations, the universe records its history. Our journey through this afterglow invites us to slow down, to absorb the subtle patterns, and to appreciate the elegance of cosmic physics. The story does not end with the CMB itself. As we move forward, we will explore how matter and light evolved after recombination, how the first stars and galaxies formed, and how the cosmic web arose. We will see how the initial conditions imprinted on the CMB grew into the complex structures we observe today. The afterglow sets the stage for this evolution, and understanding it is essential for the chapters to come. Like a soft lullaby, the cosmic microwave background hums in the background of the universe, connecting our present to its deepest past. Our next part will follow these threads into the realms where the first light was transformed by the first structures. We have wandered through the quiet afterglow of the cosmos and lingered on the gentle hum left behind by the Big Bang. Now the narrative moves from that soft radiance into a night that lasted for hundreds of millions of years. During that long darkness, the universe was a canvas of blackness, painted only by the faint whisper of hydrogen gas. Deep within that expanse, gravity was at work, drawing ever so gently on the wisps of matter, compressing them into small halos that would one day ignite into the first points of starlight. Within those halos, the primordial gas was almost pure hydrogen and helium, lacking the metals that future generations of stars would forge. Cooling was difficult because there were few atoms with which to radiate away heat. Yet even in this austere environment, molecules of hydrogen could form. Those molecules vibrated and spun, releasing little packets of energy that let the gas clouds lose their warmth. The halos gradually compressed, and as their core temperature rose, a tug of war emerged between the inward pull of gravity and the pressure of heated gas. When gravity finally won, a small protostar appeared at the center, the first tiny ember in the cosmic night. These first stars, known as the primordial generation, were unlike anything that exists today. Their lack of metals meant that they could not efficiently split into many fragments, so simulations suggest they were often massive, with typical masses tens of times that of the Sun, and in some cases perhaps 100 or more. They burned bright and hot, fusing hydrogen rapidly into heavier elements in their cores. Their lifetimes were short on cosmic timescales, ending in cataclysmic explosions, or, for the largest, in direct collapse into black holes. Yet during their brief existence, they filled the surrounding space with intense ultraviolet light. Ultraviolet photons, streaming from these luminous giants, had enough energy to rip electrons from the surrounding hydrogen, forming bubbles of ionized gas around each star. as more and more stars ignited within neighboring halos. These bubbles grew and sometimes overlapped, gradually carving out islands of transparency in the opaque sea of neutral hydrogen. The universe remained patchy, with pockets of darkness separated by expanding spheres of ionization. On the largest scales, the process resembled a patchwork quilt, slowly being stitched together, the seams representing boundaries where light had yet to penetrate. As the first stars died, their demise seeded the surrounding gas with the first heavy elements. Supernovae distributed carbon, oxygen, and other metals into the interstellar medium, changing the chemistry of the gas. Metals allow gas to cool more effectively by emitting radiation more readily, which in turn supports fragmentation into smaller clumps and leads to the formation of lower mass stars. This chemical enrichment created a feedback loop. Each new generation of stars enriched the environment further, opening new channels for star formation. The cosmic cradle was evolving from a pristine, simple composition into a more complex, life-friendly mixture. During this epoch of early starlight, we also witnessed the onset of a global transformation known as rayonization. The ultraviolet light from many sources, including massive stars and possibly early black holes, produced growing regions of ionized hydrogen. Over hundreds of millions of years, these regions expanded and merged, eventually permeating the universe. The process was not uniform. It depended on where stars formed and on how efficiently they emitted ionizing photons. Some parts of the cosmos remained neutral longer, while others cleared early, creating a mosaic of contrasting environments. Rayonization affected the structure of the cosmos in more ways than simply clearing fog. The heating of the intergalactic medium increased its pressure, making it harder for gas to fall into shallow gravitational wells. Small halos that might otherwise have formed stars were starved, while larger halos continued to accrete matter. This selective suppression influenced the distribution of galaxies, delaying the growth of some and accelerating the development of others. In this way, reionization became not just a phase transition for hydrogen, but a sculptor of cosmic architecture. Observationally, the evidence for reionization comes from several sources. The most direct is the absence of absorption features in the spectra of distant quasars beyond a certain redshift, indicating that hydrogen had become ionized and transparent to ultraviolet light. Another line of evidence is the cosmic microwave background itself. Scattering of microwave photons off free electrons during reionization left subtle imprints that can be measured today. Combined, these observations suggest that reionization completed roughly 1 billion years after the Big Bang, though its exact timeline remains an area of active research and curiosity. To understand the detailed pattern of ionized and neutral regions during reionization, astronomers look to the faint whisper of a particular radio line emitted by neutral hydrogen. This line arises from a subtle flip in the alignment between the proton and electron spins in a hydrogen atom. When the spins change from parallel to antiparallel, the atom emits a photon with a wavelength of about 21 centimeters. That wavelength is stretched by cosmic expansion to meter-long waves by the time it reaches modern radio telescopes. Mapping this signal is extraordinarily challenging. The emitted radiation is faint and must be extracted from a background many orders of magnitude brighter. Additionally, human-made radio interference and Earth's own ionosphere can mask the cosmic whisper. Researchers build arrays of antennas in remote deserts or on the moon's far side to escape noise, and they use sophisticated algorithms to separate the cosmological signal from foregrounds. If successful, These efforts promise a three-dimensional movie of the cosmic dawn, showing how neutral hydrogen flowed around ionized bubbles as the first light spread. Meanwhile, another structural phenomenon was also unfolding: the assembly of the cosmic web. The same gravitational pull that drew matter into the first halos continued to shape the universe on larger scales. Dark matter, which interacts only gravitationally and comprises the bulk of the mass, formed an intricate network of filaments and sheets. These structures crisscrossed the cosmos, with intersections forming denser nodes that would later host galaxies and clusters of galaxies. Between the filaments were vast voids, regions containing relatively little matter. At early times, baryonic gas fell into the gravitational potential wells carved by dark matter. It flowed along filaments, collected in nodes, and then cooled and condensed to form stars. Simulations portray this cosmic web as an almost organic mesh, resembling the structure of foam or a network of soap bubbles frozen in time. The filaments are the boundaries of giant voids, and at the nodes where multiple filaments meet, matter accumulates to the point where galaxies and clusters can form. This architecture provides the scaffolding upon which luminous matter is distributed. Understanding the cosmic web requires both theoretical insight and observational evidence. Computer simulations track billions of particles representing dark matter and gas, tracing their movements under gravity over billions of years. The resulting patterns match observations remarkably well, reproducing the filamentary network and the distribution of galaxies. Observationally, surveys of galaxies and gas in the local universe reveal similar structures, while large-scale maps of the cosmic microwave background show early seeds of the web imprinted as tiny fluctuations in density. In this sense, the cosmic web is both predicted and seen, a testament to the power of gravity acting over enormous distances. The cosmic web is dynamic. Gas flows along filaments into nodes, fueling star formation and feeding supermassive black holes. When galaxies form, they do not grow in isolation, but receive continuous streams of fresh gas along these channels. Sometimes filaments deliver entire small galaxies into larger systems, resulting in mergers that can trigger bursts of star formation. The interplay between smooth accretion and violent mergers shapes the properties of galaxies, making the cosmic web not just a static scaffold, but a living, evolving network. Another natural phenomenon reveals the distribution of mass in the cosmic web: gravitational lensing. According to general relativity, mass curves the fabric of space and time, and light traveling through this curvature follows bent paths. When a massive object lies between a distant source and the observer, the light from the source can be distorted, magnified, or even split into multiple images. On cosmic scales, entire galaxy clusters act as lenses, bending the light of more distant galaxies behind them. Strong gravitational lensing produces dramatic effects. Light from a faraway galaxy may appear as multiple spots or elongated arcs around the lensing mass. In some cases, if the alignment is nearly perfect, an Einstein ring forms, a circle of light encircling the foreground lens. These spectacular configurations not only provide aesthetic beauty, but also act as natural telescopes, magnifying the background sources. Because of lensing, astronomers can study galaxies that would otherwise be too faint or too distant to be seen with current instruments. Weak gravitational lensing is subtler. Instead of producing obvious arcs, it slightly distorts the shapes of many background galaxies by stretching them in a coherent direction. By measuring these tiny shape changes across millions of galaxies, researchers can map the distribution of mass, including dark matter, on large scales. This technique has become a powerful probe of the cosmic web and cosmological parameters, complementing observations from galaxy surveys and the cosmic microwave background. It provides an indirect way to see invisible matter by its influence on light. There is also the phenomenon of microlensing, where smaller masses, such as stars or planets, act as lenses. Microlensing events can reveal the presence of objects that emit little or no light themselves, such as planets around distant stars or isolated black holes wandering through space. Although microlensing occurs on much smaller scales than the structures we have been discussing, it reflects the same fundamental principle. Mass tells light how to travel, and careful observation of that travel yields information about mass. Gravitational lensing has another important role in the study of the early universe. Because lensing magnifies distant objects, it allows telescopes to peer further back in time than they otherwise could. Massive galaxy clusters serve as cosmic magnifying glasses, boosting the brightness of galaxies from the cosmic dawn. Some of the first galaxies, seen by the James Webb Space Telescope, owe their detectability to lensing by intervening clusters. By combining lensing with deep observations, astronomers push the boundaries of what is observable. Over the past few decades, astronomers have also used space telescopes to create unprecedentedly deep images of small regions of the sky. One of the most iconic of these is the Hubble Deep Field, a long exposure taken in the mid-1990s that revealed thousands of distant galaxies within a tiny patch of sky. Many of these galaxies appeared as small smudges, each representing an entire island universe. Because light takes time to travel, looking at these faint smudges is equivalent to looking back in time, seeing galaxies as they were billions of years ago. The Hubble Deep Field was followed by even deeper images, such as the Hubble Ultra Deep Field. By integrating light over many days, astronomers captured a view containing about 10,000 galaxies, including some of the earliest known. These early galaxies were often small and irregular, resembling toothpicks or beads, hinting at an era when galaxies were assembling and merging. The ultra-deep observations also showed that black holes nestled at galaxy centers grew alongside their host galaxies, suggesting a connection between galaxy formation and black hole evolution. Subsequent campaigns extended the reach into the near-infrared, enabling the observation of galaxies whose light has been stretched by cosmic expansion into redder wavelengths. One such view uncovered galaxies that were already forming stars vigorously about 600 to 750 million years after the Big Bang. In these objects, star formation rates increased rapidly, indicating that the early universe experienced a brief but intense phase of galaxy building. These findings pushed the known frontier of cosmic history further back, revealing a period of rapid transformation. Another image, the Hubble E Extreme Deep Field, combined 10 years of observations to produce the deepest view yet. It contains thousands of galaxies, some so faint that they are 10 billion times dimmer than the faintest stars visible to the naked eye. These galaxies are snapshots of the universe when it was very young, often caught in the act of merging or streaming into larger structures. Through such ultra-deep images, we witness the diversity of early galaxies and the processes by which they grew. Taking deep images is not just about seeing the farthest objects. It is also about counting them. Astronomers use deep fields to measure the number of galaxies as a function of their brightness, a relationship known as the luminosity function. The distribution typically shows that there are many more faint galaxies than bright ones. At low redshift, This distribution can be described by a mathematical form called the Schechter function, which rises toward faint luminosities and then falls off at the bright end. At high redshift, measuring the luminosity function becomes more challenging, as telescopes push to detect fainter and fainter galaxies. The observations become incomplete. Objects with low brightness are more likely to be missed, and selection effects can distort the apparent distribution. To correct for this, astronomers use simulations that populate mock universes with galaxies and then apply the same detection criteria. These corrections can significantly affect the inferred number of faint galaxies and thus the slope of the luminosity function. The slope at the faint end of the luminosity function is particularly important. If the slope is steep, meaning there are many faint galaxies, then those galaxies could contribute a significant fraction of the photons needed to complete reionization. In some analyses, the slope approaches a value near -2, which implies that the total light output becomes sensitive to where the luminosity function is cut off. Small differences in the faintest detectable galaxies can then lead to large differences in the inferred cosmic star formation rate. Observations of high redshift galaxies suggest that the faint end slope steepens with increasing redshift. Between redshifts 5 and 7, the slope is around -1.7, indicating a growing population of small galaxies. There is also evidence that the characteristic luminosity decreases with redshift, meaning that typical galaxies were dimmer in the early universe. However, these conclusions are subject to uncertainties due to the small sample sizes and the effects of cosmic variance, where different regions of the sky may have different galaxy densities. Although the details are still debated, it is clear that faint galaxies played a crucial role in cosmic history. They were numerous, likely forming stars at a steady pace, and their collective light helped to transform the universe from neutral to ionized. Future telescopes will probe even deeper, revealing the smallest galaxies that existed during the cosmic dawn. As they do, our understanding of the contribution of faint galaxies to reionization will sharpen, and the story of early star formation will become more complete. Beyond counting galaxies, astronomers must also consider how galaxies regulate their own growth. One of the most important mechanisms involves winds driven by intense star formation. When massive stars end their lives as supernovae, they release enormous amounts of energy into their surroundings. This energy can push gas out of galaxies, generating powerful outflows. These winds carry away the raw material needed to form new stars, temporarily slowing or even halting star formation. Observations have detected such winds in galaxies near and far. In some starburst galaxies, these winds blow at hundreds of kilometers per second, launching molecular gas into the halo or even into intergalactic space. In the early universe, similar processes likely occurred. Recent observations using millimeter-wave telescopes have detected winds in galaxies that existed when the universe was less than 2 billion years old. The winds in these galaxies appear to be venting hydroxyl molecules and other star-forming material, revealing that feedback mechanisms were already at work. These observations rely on the synergy of different tools. Gravitational lensing can magnify distant galaxies, making it possible to detect faint emissions from molecules carried by winds. Sensitive radio and submillimeter telescopes, such as ALMA, can then measure the speeds and masses of outflowing gas. By combining lensing and modern instrumentation, astronomers can study the dynamics of galaxies at times when they were forming stars vigorously. In doing so, they learn how galaxies regulate their growth and how feedback affects their evolution. Another form of feedback comes from black holes. Supermassive black holes reside at the centers of many galaxies, and can power quasars when they accrete gas. The energy released by accretion can drive jets and radiation that heat or expel surrounding gas. This process, called active galactic nucleus feedback, can suppress star formation in the host galaxy. In the early universe, the first black holes likely grew rapidly, and their feedback could have shaped the assembly of the earliest galaxies. In addition to winds and black holes, chemical feedback plays a role in galactic evolution. When stars explode, they enrich the gas with heavy elements. These metals allow the gas to cool more efficiently, leading to the formation of smaller, more numerous stars in subsequent generations. Metals also enable molecules like carbon monoxide and dust grains to form. Dust absorbs ultraviolet light and re-radiates it in the infrared, affecting the thermal balance of the interstellar medium and providing surfaces on which complex molecules can assemble. The presence of metals and dust in very early galaxies has been a topic of intense interest. Until recently, astronomers assumed that heavy elements took hundreds of millions of years to build up to significant levels. However, recent observations challenge this assumption. The James Webb Space Telescope detected carbon in a galaxy just 350 million years after the Big Bang, suggesting that some stars produced heavy elements much sooner than expected. This rapid enrichment implies efficient star formation and perhaps different kinds of stars than those seen in the later universe. Metals like carbon are essential, not just for cooling, but also for life as we know it. Carbon can form complex molecules, and carbon-rich dust can clump together to form larger, solid bodies. The early appearance of carbon hints that the ingredients for rocky planets and potentially life may have been present in some regions soon after the first stars. Such discoveries fuel speculation about when and where the first habitable environments could have emerged, adding a philosophical dimension to the study of cosmic dawn. Another surprising discovery is that some early galaxies were already chemically mature. Observations of a lensed system revealed two galaxies orbiting each other just 1.4 billion years after the Big Bang. One of them, though small, possessed metallicity similar to the Sun's and contained dust, implying that several generations of star formation had already occurred. This galaxy was part of a more complex system that included a larger neighbor and a dark matter halo, indicating a rich environment. Such mature chemistry, so soon after the cosmic dawn, suggests rapid star formation and efficient recycling of gas. Dust in the early universe not only tells us about star formation, it also affects how we observe galaxies. Dust grains absorb ultraviolet and visible light and re-emit it in the infrared. If a galaxy contains a lot of dust, its light may be obscured at short wavelengths, making it difficult to detect with optical telescopes. This means that some of the earliest and most intense star-forming galaxies might be hidden from view in optical deep fields, requiring infrared observations to uncover them. The interplay between gas, dust, and radiation thus shapes the observable universe. Galaxies form stars from gas that cools and condenses. Those stars then produce radiation and winds that can heat the gas or blow it away, while also synthesizing metals and dust. Dust then alters the flow of radiation, affecting cooling and star formation. This complex feedback loop operates on all scales, from individual stars to galaxy clusters, and is crucial for understanding how structures grow over cosmic time. As we contemplate these processes, it is worth remembering that our own existence is intimately connected to them. The atoms in our bodies were forged in stars, like those early giants. The carbon and oxygen we breathe came from generations of supernovae that enriched their surroundings and seeded new star systems. Without the feedback mechanisms that distribute these elements, planets like Earth would not exist. When we study the cosmic dawn, we are in a sense looking at our own distant ancestry. Our journey through this part of the story continues to unfold. We have looked at how the first stars formed in dark halos, how their light carved out bubbles of ionization and ended the cosmic night, and how the universe became transparent. We have explored the cosmic web that supports galaxies, and the natural telescopes of gravity that let us see faraway times. We have dived into the deepest images to count faint galaxies and considered how their numbers shape our understanding of ionization. And we have examined the winds, metals, and dust that regulate galactic growth and hint at the earliest building blocks of life. Yet the narrative is far from complete. The cosmic web continues to evolve, and galaxies continue to merge and grow. The next part will carry us through later epochs, where structures mature and the universe takes on a more familiar shape. For now, we leave the dawn behind, gently carried forward by the momentum of time, ready to witness the next chapters in the grand evolution of the cosmos. The long night that preceded the first stars was not completely featureless. Tiny ripples in the density of matter, imprinted by quantum fluctuations during inflation, provided the seeds around which gas could gather. In the absence of starlight, the gas was cold and neutral, and its temperature slowly declined as the universe expanded. This cooling favored the formation of molecular hydrogen, but the formation of such molecules was slow and inefficient. Nevertheless, even small amounts were enough to allow gas clumps to radiate away energy and begin collapsing into halos. In these halos, the interplay between gravity, pressure, and angular momentum determined whether a single massive protostar would form or whether the cloud would fragment into several pieces. Simulations show that turbulence generated by accretion flows can create density fluctuations within the collapsing cloud. Some of these fluctuations may collapse to form secondary protostars, leading to multiple star systems. However, without dust and heavy elements, the ability of the gas to cool is limited, and fragmentation is less likely than in later epochs. As a result, the first stars tended to be more massive and rarer than their modern counterparts. As soon as the first stars ignited, they transformed their surroundings. The intense ultraviolet radiation not only ionized hydrogen, but also dissociated molecular hydrogen in nearby clouds, preventing further cooling. This created a feedback effect. Early star formation could suppress subsequent star formation in neighboring halos by destroying the very molecules needed to cool the gas. However, the violent death of these stars also compressed nearby gas via shockwaves from supernovae, potentially triggering new collapses. The balance between suppression and triggering determined how quickly star formation propagated. Massive stars generate strong stellar winds even before they explode. These winds carry mass and momentum away from the star, carving cavities in the surrounding gas. The density of gas near the star decreases, and the cavity fills with hot, ionized gas. When the star eventually explodes as a supernova, its shockwave expands more freely into this low-density environment, reaching farther and mixing metals into a larger volume. This preconditioning by stellar winds can amplify the impact of supernova explosions on galactic surroundings. The end states of the first stars depend on their mass. Stars below about 100 solar masses likely ended as core collapse supernovae, leaving behind neutron stars or black holes. More massive stars may have collapsed directly into black holes without a bright explosion, while others could have experienced pair instability supernovae, completely disrupting themselves and ejecting their entire mass. Each of these pathways contributed differently to the chemical enrichment of the cosmos. Pair instability explosions, for example, synthesized large amounts of intermediate mass elements, but little iron, while core collapse supernovae produced heavier elements including iron and nickel. The black holes left by the first stars could have become seeds for later supermassive black holes. In dense regions where gas inflow was high, these seeds might have grown rapidly by accreting gas and merging with other black holes. Observations of quasars at redshifts greater than 6, powered by black holes with masses of 1 billion solar masses, suggest that black hole growth must have been efficient in the early universe. Whether this growth occurred primarily through accretion or through the merger of many smaller black holes remains a topic of investigation. Either way, the first stars played a crucial role by providing the initial mass and gravitational potential wells needed for this process. The bubbles of ionized gas carved by the first stars did not expand indefinitely. As stars died and their light faded, recombination occurred. Free electrons combined with protons to form neutral hydrogen again. The recombination time depends on density, so dense regions recombined faster than diffuse ones. Recombination emitted photons that could further cool the gas, aiding subsequent star formation. This cycle of ionization and recombination added complexity to the early intergalactic medium, creating regions of varying ionization states and temperatures. As more sources of ionizing radiation appeared, the ionized bubbles grew larger. Eventually, some bubbles overlapped, forming networks of ionized regions separated by neutral filaments and pockets. The geometry of these regions depended on the distribution of sources and the density field. Simulations show that reionization proceeded in a patchy manner, with high-density regions reionizing early because they hosted more sources, while low-density voids could remain neutral for longer. The patchiness influenced the temperature and state of the gas, affecting subsequent accretion onto halos. The completion of reionization marked a global phase transition. Once the average hydrogen atom was ionized, the universe became transparent to ultraviolet photons. The intergalactic medium became heated to temperatures of tens of thousands of degrees, raising the Jeans mass, the minimum mass for a gravitationally bound gas cloud, to overcome pressure and collapse. Halos below this mass could not readily accrete gas or form stars. This suppression shaped the mass function of galaxies and contributed to the relative scarcity of low-mass galaxies compared with predictions from dark matter alone. To measure reionization directly, astronomers turned to the spectra of distant quasars. When light from these luminous objects passes through clouds of hydrogen gas, it is partially absorbed at specific wavelengths, corresponding to transitions in hydrogen. The pattern of absorption lines, known as the Lyman alpha forest, encodes information about the distribution and state of hydrogen along the line of sight. At high redshifts, the forest thickens, and eventually, a dark trough appears where the universe is opaque. The disappearance of this Gunn-Peterson trough at later times indicates the completion of reionization. Another key observable is the Thomson scattering optical depth measured from the cosmic microwave background. Free electrons during reionization scattered microwave photons, smoothing out temperature anisotropies on small angular scales and introducing polarization patterns on large scales. By analyzing these signatures, researchers estimate the integrated column of free electrons and hence the timing and duration of reionization. Current measurements suggest that reionization was extended, beginning as early as redshift 15 and ending by redshift 6. However, the exact history is uncertain, and different models can reproduce the observed optical depth. Radio telescopes designed to detect the 21-centimeter line of neutral hydrogen operate differently from optical telescopes. Instead of focusing light onto a camera, arrays of antennas measure the correlation of signals arriving at different baselines. These correlations, or visibilities, can be combined through interferometry to reconstruct images or, more commonly, statistical measures of the hydrogen distribution. Foreground subtraction is a major challenge because emission from our galaxy and other astrophysical sources is many times brighter than the cosmological signal. Sophisticated calibration and data analysis techniques are required to extract the faint imprint of rayonization. Current experiments, such as the hydrogen epoch of rayonization array and LOFAR, are already providing upper limits on the power spectrum of the 21 centimeter signal. Planned arrays like the square kilometer array promise to produce detailed maps of the distribution of neutral hydrogen and its evolution over time. These observations will complement other probes of rayonization, providing a three-dimensional view of how the first luminous structures interacted with their environment. By combining radio, optical, and microwave observations, astronomers hope to untangle the complex interplay of sources, feedback, and gas dynamics during the dawn of galaxies. The cosmic web itself traces back to small fluctuations in the density field laid down during inflation. These fluctuations grew over time as gravity amplified the differences between slightly overdense and underdense regions. In overdense regions, matter slowed its cosmic expansion and began to collapse, forming sheets and filaments. In underdense regions, matter flowed away, creating voids. The pattern of collapse proceeds hierarchically. Sheets form first, then filaments, and finally nodes at the intersections of filaments. The anisotropic nature of this collapse leads to the characteristic shapes seen in simulations and observations. Along one dimension, matter may collapse faster than along others, forming a pancake-like sheet. Later, as collapse continues along a second dimension, the sheet becomes a filament. Finally, collapse along the third dimension forms a dense node. These stages are sometimes described using the Zeldovich approximation, which approximates the trajectories of fluid elements in the early universe. Although simplified, this picture captures the essence of cosmic structure formation. The cosmic web not only provides the initial conditions for galaxy formation, but also influences the shapes and spins of galaxies. Gas accreted along filaments can impart angular momentum to halos, aligning their spin axes with the filaments. Observations have suggested that the orientation of galaxy disks correlates with the direction of nearby filaments, reflecting this relationship. In addition, the flows of gas along filaments can sustain star formation over extended periods, delivering fresh material to galactic centers. Without these flows, galaxies would exhaust their gas more quickly and become passive. At the largest scales, the cosmic web can be mapped using the distribution of galaxies and the Lyman alpha forest. Techniques such as tomography reconstruct the three-dimensional distribution of hydrogen by observing the absorption along many different lines of sight. Combined with gravitational lensing maps and galaxy surveys, these techniques reveal the underlying dark matter structure. The resulting picture shows that the universe is interconnected. No galaxy exists in isolation, but is part of a vast network, each node linked by filaments spanning tens or hundreds of millions of light years. Within this network, galaxies undergo a variety of interactions. Some merge with their neighbors, driven by dynamical friction and torques in dense environments. Mergers can dramatically transform galaxies, turning disks into spheroids, triggering starbursts and feeding central black holes. Other interactions are more subtle. Tidal forces from passing galaxies can distort shapes, induce spiral arms, or strip gas from the outskirts. These interactions contribute to the diversity of galactic morphologies seen today. As we observe gravitational lensing on larger samples, we gain an increasingly precise measurement of cosmic structure. Surveys like the Dark Energy Survey and the hypersuprime cam survey map weak lensing signals across thousands of square degrees. These maps provide constraints on the matter density of the universe and the growth of structure over time. By comparing observations with predictions from different cosmological models, researchers test theories of dark energy, modified gravity, and the nature of dark matter. Thus, lensing has become a cornerstone of modern cosmology. Gravitational lensing also allows the measurement of the Hubble constant through time delays. In systems where a quasar or supernova is lensed into multiple images, the paths taken by light have different lengths. Variations in the brightness of the source appear in each image at different times. By measuring these time delays and modeling the mass distribution of the lens, astronomers can infer the expansion rate of the universe. This method is independent of local distance ladders and provides a complementary approach to measuring cosmic expansion. In addition to lensing by galaxies and clusters, there is lensing by the cosmic web itself. Weak lensing by large-scale structure subtly distorts the cosmic microwave background's polarization and temperature patterns. The Planck and Atacama cosmology telescope experiments have detected these distortions, and future missions will map them with greater precision. Such observations help to trace the distribution of mass throughout cosmic history and to test models of neutrino masses, dark matter properties, and inflationary physics. While lensing offers glimpses of distant galaxies, deep field imaging fills in details. With the advent of the James Webb Space Telescope, new deep fields reveal galaxies whose light has been traveling for more than 13 billion years. These observations reach beyond what Hubble could see, detecting galaxies that are fainter and more distant. Some of these galaxies show surprisingly mature features, such as well-developed disks and red colors, indicative of older stellar populations. These discoveries challenge models that predicted only small, irregular systems at such early times. The design of deep fields involves careful consideration of the field's location and the wavelengths used. Astronomers choose areas of sky far from bright stars or regions of high galactic foreground to minimize contamination. They also select filters that sample key spectral features, such as the Lyman break, to identify high redshift galaxies. By stacking many exposures in different filters, they build up sensitivity across a broad range of wavelengths. The resulting images not only reveal individual galaxies, but also allow estimates of their redshifts, masses, and star formation rates. As deep fields become deeper, they encounter the limits of current technology. The faintest galaxies contribute only a few photons per day to a telescope's detector. Detecting such faint sources requires long integration times and careful control of noise. Space telescopes avoid the blurring effects of Earth's atmosphere, but they still contend with cosmic rays and instrumental effects. The planning and processing of deep field observations are therefore as critical as the observations themselves. Beyond simply counting galaxies, deep fields provide insight into the distribution of galaxy properties. By analyzing colors and spectral energy distributions, astronomers classify galaxies into star-forming, quiescent, and dusty categories. At high redshift, most galaxies are actively forming stars, but quiescent galaxies begin to appear surprisingly early. The presence of massive, dead galaxies at Z around 4 or 5 suggests that some systems quenched their star formation quickly, possibly due to feedback from black holes or environment. Understanding how and why galaxies quench is a key question in galaxy evolution. Deep fields also highlight the role of environment in galaxy growth. Regions of higher density host more massive galaxies and clusters, while voids contain fewer, smaller systems. By comparing the properties of galaxies in different environments at the same epoch, Researchers infer how environment influences star formation, morphology, and chemical evolution. These comparisons show that environment matters even at early times, although intrinsic properties and feedback also play strong roles. The luminosity function provides a statistical summary of galaxy populations. Parameters like the characteristic luminosity and number density change with cosmic time, reflecting the evolving balance between star formation and quenching. By combining luminosity functions across a range of redshifts, astronomers piece together the cosmic star formation history. This history reveals that star formation peaked around redshift 2, when the universe was about 3 billion years old, and has declined since then. Understanding this decline requires a combination of internal feedback processes and external factors like gas accretion and environment. The steepness of the faint end slope of the luminosity function at very high redshift remains a matter of debate. Some observations suggest that the slope may be as steep as -2, indicating a huge number of faint galaxies. If true, these galaxies could dominate the ionizing photon budget necessary for reionization. Other studies find flatter slopes, suggesting fewer faint galaxies and implying that brighter galaxies or other sources such as quasars contribute more. Resolving this issue will require deeper surveys and improved completeness corrections. Completeness corrections attempt to account for galaxies that lie below the detection threshold. These corrections depend on assumptions about the shapes, sizes, and surface brightness distributions of faint galaxies. If the assumptions are incorrect, the inferred number of faint galaxies could be biased. For example, if very faint galaxies are more diffuse than expected, they might escape detection more readily, leading to underestimates of their abundance. Conversely, if they are more compact, the corrections could overcompensate, inflating their numbers. Observational biases also affect the measurement of galaxy luminosities. Dust within galaxies can attenuate starlight, especially at ultraviolet wavelengths. If dust is more prevalent in some galaxies than others, it can make them appear dimmer and shift them into lower luminosity bins. Similarly, gravitational lensing by intervening mass can magnify or demagnify galaxies, altering their apparent brightness. Careful analysis must separate these effects from intrinsic luminosity to obtain an accurate luminosity function. In the context of feedback, winds driven by star formation play a crucial role in shaping the faint end slope. If winds efficiently remove gas from small galaxies, they can limit the amount of stars these galaxies form, reducing their luminosities. This would flatten the luminosity function at the faint end. Conversely, if feedback is weaker, small galaxies may continue forming stars, steepening the slope. The diversity of wind strengths and efficiencies across galaxies adds complexity to this picture. Feedback from massive stars and supernovae not only regulates star formation, but also influences the intergalactic medium. Outflows can transport metals into the space between galaxies, enriching it and altering its cooling properties. These metals can condense onto dust grains, facilitating the formation of molecules like carbon monoxide, which further cools the gas. Enriched gas falling back into galaxies can fuel new rounds of star formation, creating a cycle of outflow and inflow. The balance between ejection and recycling determines how quickly galaxies build up mass and metals. The detection of carbon in a galaxy at Z around 13 by the James Webb Space Telescope underscores how rapidly chemical enrichment can occur. Carbon may be produced by certain types of massive stars and distributed into the interstellar medium through winds and supernovae. The presence of carbon dust suggests that these processes operated efficiently within a few 100 million years. Such early enrichment challenges models that delay significant metal production until later times. It also opens new possibilities for the formation of complex organic molecules in the early universe. The discovery of chemically mature galaxies at Z around 4 also speaks to efficient star formation and feedback. For a galaxy to reach solar metallicity by that time, it must convert gas into stars at a high rate and retain the metals produced. Winds must not be so strong as to blow all the metals away, yet not so weak as to allow unchecked star formation. This delicate balance may be influenced by environment, mass, and the presence of a massive neighbour. Such galaxies provide laboratories for testing models of early galaxy evolution. Dust production in the early universe likely arises from multiple sources. Core collapse supernovae can produce dust grains in their expanding ejecta, although reverse shocks may destroy some fraction. Asymptotic giant branch stars, which contribute significantly to dust in the local universe, may not have had time to evolve in the first billion years. Therefore, dust detected in very high redshift galaxies may originate predominantly from supernova. Understanding dust production mechanisms helps to interpret infrared observations and the thermal emission from early galaxies. Galactic winds carry dust out into the circumgalactic and intergalactic medium. Radiation pressure on dust grains can accelerate them away from star-forming regions. Once outside, dust can survive for long times, affecting the thermal balance of the surrounding gas and providing surfaces for further chemical reactions. Dust in the intergalactic medium also influences the propagation of ultraviolet and optical light, leading to intergalactic extinction that must be accounted for when interpreting observations. High redshift winds observed by ALMA reveal that outflows can reach hundreds of kilometers per second. At such velocities, gas can escape the gravitational potential of small galaxies, depositing metals and dust far from their origin. These outflows can manifest as broad absorption or emission lines in spectra, indicating the presence of molecules like hydroxyl or carbon monoxide moving at high speeds. The detection of these lines in galaxies, observed less than 2 billion years after the Big Bang, shows that feedback processes were well established early on. Gravitational lensing plays a vital role in studying these early winds. Without the magnification provided by a foreground cluster, the faint emissions from distant galaxies would be below the detection threshold. Lensing effectively enlarges and brightens the image, enabling telescopes to resolve structures and kinematics within the galaxy. By observing multiple lensed images, astronomers can confirm that the signals are not artifacts and can reconstruct the source's intrinsic properties. This synergy between lensing and instrumentation exemplifies how cosmic coincidence aids our exploration. The study of early feedback processes informs our understanding of the mass-metallicity relation. In the local universe, more massive galaxies tend to have higher metallicities because their deeper gravitational potentials retain metals more effectively. At high redshift, the relation may have a similar slope, but lower normalization, reflecting the shorter time available for enrichment. Observations of high redshift galaxies allow us to test whether the same physical processes govern the relation across cosmic time. Deviations may indicate differences in wind strength, star formation efficiency, or gas inflow rates. As we piece together the story of how galaxies form, regulate, and evolve, we also see how intimately these processes are tied to the broader cosmic environment. The cosmic web delivers gas and merges small halos into larger ones. Reionization sets the thermal state of the intergalactic medium, influencing which halos can form stars. Feedback from stars and black holes enriches and redistributes matter, shaping future generations of stars. Each part of the story feeds into the next, creating a tapestry of interactions that govern the evolution of structure. In the narrative of cosmic dawn, there is a constant interplay between simplicity and complexity. The underlying physics is rooted in gravity, atomic transitions, and thermodynamics, concepts that are straightforward at their core. Yet the outcomes of these processes lead to structures of immense diversity and beauty. The first stars and galaxies were not uniform, but varied in mass, composition, and environment. Through feedback and merging, they evolved into the rich zoo of galaxies we see today. This complexity makes the study of the early universe both challenging and rewarding. Observational limitations mean that we often see only a small part of the story, while theoretical models must incorporate many interacting processes. Numerical simulations serve as laboratories where different physical parameters can be varied to study their effects. Observations then test these models, refining our understanding. This iterative process of hypothesis, simulation, and observation lies at the heart of modern astrophysics. Even within individual halos, the formation of the first stars involved detailed substructures. Gas collapsing toward the center began to spin, forming a disk around the protostar. Within this disk, gravitational instabilities could lead to fragmentation, creating secondary stars in orbit around the primary. Radiative feedback from the central star heated the surrounding gas, suppressing further fragmentation and favoring the growth of the primary. This interplay between disk physics and radiation influenced the final mass and multiplicity of the first stars. The coupling between the 21-centimeter signal and the cosmic microwave background depends on the spin temperature of hydrogen. During the Dark Ages, collisions between hydrogen atoms dominated and drove the spin temperature toward the gas temperature. As the first stars turned on, they emitted ultraviolet photons that resonantly scattered off hydrogen, coupling the spin temperature to the color temperature of the radiation field. This Wouthuysen field effect allowed the 21-centimeter line to appear in absorption against the microwave background. Later, when the gas heated, the signal transitioned to emission, tracing the evolution of temperature and ionization. Observations of Lyman alpha emitters provide another window into ionization. These galaxies are identified by their strong emission in the hydrogen Lyman alpha line. However, this line is easily scattered by neutral hydrogen in the intergalactic medium, making its transmission sensitive to the ionization state. At high redshift, a decline in the number of Lyman alpha emitters and in the strength of their lines suggests increasing neutral hydrogen fraction. By comparing Lyman alpha observations with measurements of continuum-selected galaxies, astronomers trace the progression of rayonization and the clustering of ionized regions. Rayonization occurred not only for hydrogen, but also for helium. The first ionization of helium happened alongside hydrogen because the ionization energies are similar. However, the second ionization of helium, which requires higher energies, likely occurred later, driven by hard ultraviolet and X-ray photons from quasars. This helium-2 rayonization heated the intergalactic medium further and created additional spectral signatures. The timing of helium rayonization provides clues about the growth of supermassive black holes and the spectrum of ionizing sources. Morphologies of early galaxies are often irregular and clumpy. Without well-settled disks, star formation occurs in pockets scattered across the galaxy. Gas dynamics are dominated by turbulence and inflow from filaments, leading to thick, dispersion-dominated structures. Over time, these systems can stabilize into rotating disks as gas settles and angular momentum is redistributed. The transition from chaotic clumps to ordered disks marks an important stage in galaxy evolution and may be influenced by feedback, mergers, and environment. Some of the earliest bound stellar systems may have survived to the present day as globular clusters. These dense clusters of old stars orbit in the halos of galaxies and have ages exceeding 12 billion years. Their metallicities are low, indicating that they formed early from relatively unenriched gas. The formation of globular clusters could have been triggered by the same processes that built the first galaxies, perhaps in the dense regions of early mergers. Studying globular clusters thus provides another link to the conditions of the cosmic dawn. At slightly later times, protoclusters, the progenitors of modern galaxy clusters, began to take shape. These regions contain overdensities of galaxies and gas that will eventually collapse into massive clusters. Protoclusters at redshifts of 2 to 6 have been identified through surveys of star-forming galaxies and quasars. Their study reveals that cluster formation is an extended process, with galaxies growing and interacting within a common dark matter halo. Observing protoclusters helps to understand how environment influences the growth of galaxies and the build-up of large-scale structures. Magnetic fields are ubiquitous in galaxies today, but their origin in the early universe is still an open question. Seed magnetic fields may have been generated during cosmic inflation or phase transitions, or they may have arisen from plasma instabilities during structure formation. These weak fields could have been amplified by turbulence and shear flows in the first galaxies. Once established, magnetic fields influence gas dynamics, star formation, and the propagation of cosmic rays. Detecting primordial magnetic fields through observations of the cosmic microwave background or radio polarization is a frontier of cosmology. Light neutrinos, with their tiny masses, also play a role in cosmic structure. Because they travel at relativistic speeds early on, they free stream out of overdensities, damping the growth of small-scale fluctuations. The total mass of neutrinos affects the amplitude of the matter-power spectrum on small scales. Precise measurements of weak lensing and galaxy clustering can constrain the sum of neutrino masses. Thus, cosmology provides a way to probe fundamental particle properties through their imprints on the large-scale structure. The imprint of baryon acoustic oscillations provides a standard ruler for measuring cosmic distances. In the early universe, interactions between photons and baryons produced sound waves that propagated through the plasma. When recombination occurred, these sound waves froze into a characteristic scale imprinted on the distribution of matter. By measuring the clustering of galaxies and the Lyman alpha forest at this scale, astronomers can infer the expansion history of the universe. The baryon acoustic oscillation scale serves as a key tool in constraining dark energy and the curvature of space. As gas cycles through galaxies, it follows a complex pathway. Gas accretes from the intergalactic medium, cools, and forms stars. Stars then return material to the interstellar medium through winds and supernovae. This enriched gas may form the next generation of stars, or be expelled as a wind. Over billions of years, this cycling builds up the metallicity of galaxies and affects their star formation histories. Understanding the baryon cycle is essential for explaining the observed properties of galaxies across cosmic time. Cosmic rays, high-energy particles accelerated by supernovae and other energetic events, also interact with the interstellar and intergalactic medium. In the early universe, cosmic rays could have provided additional heating and ionization, especially in regions shielded from ultraviolet radiation. They may have influenced the chemistry of the gas by ionizing molecules and catalyzing reactions. The role of cosmic rays in early star formation is uncertain, but their presence adds another layer of complexity to the feedback processes shaping galaxies. The seeds of supermassive black holes may have formed not only from stellar remnants, but also through direct collapse of gas. In this scenario, A massive gas cloud collapses under its own gravity, without fragmenting, forming a black hole with a mass of thousands to hundreds of thousands of solar masses. Conditions for direct collapse require strong radiation backgrounds to suppress fragmentation and a rapid inflow of gas. Such massive seeds would grow more quickly into the billion solar mass black holes seen at high redshift. Searching for signatures of direct collapse black holes is an active area of research. As ionization progressed, it left an imprint on the cosmic microwave background beyond simple scattering. Energy injected by ionization heated electrons, leading to Compton scattering that shifted the spectrum of the microwave background slightly toward higher energies. These Y distortions are extremely small, but could be detected by future missions. Measuring spectral distortions would provide a direct window into the thermal history of the universe, including the timing and energetics of reionization and other heating events. Cross-correlating 21-centimeter observations with galaxy surveys offers a powerful way to overcome challenges faced by each method alone. Galaxies trace the locations of dense regions and ionizing sources, while the 21-centimeter signal traces neutral gas. By comparing these maps, researchers can better understand the relationship between sources and the surrounding medium. Cross-correlation can also help remove foreground contamination by isolating signals that are common to both datasets. This approach will be important for extracting cosmological information from upcoming observations. Gamma-ray bursts, the most energetic explosions in the universe, are potential probes of the early universe. Some long gamma-ray bursts are thought to result from the deaths of massive stars. Because they are visible across great distances, detecting a gamma-ray burst from the cosmic dawn would provide direct evidence of massive star formation. The afterglow spectrum of a high redshift gamma-ray burst would also reveal the state of the intervening intergalactic medium. While such events are rare, ongoing monitoring by satellites holds the promise of catching one from the earliest epochs. Gravitational waves offer another avenue to explore the early universe. Mergers of black holes and neutron stars produce ripples in spacetime that travel virtually unimpeded across cosmic distances. Detectors like LIGO and Virgo have already observed mergers at relatively low redshifts. In the future, space-based detectors like LISA may detect mergers involving black holes formed during the cosmic dawn. Additionally, a stochastic background of gravitational waves from processes like cosmic strings or phase transitions in the early universe could imprint a faint but detectable signature. Gravitational waves thus open a new window on phenomena inaccessible to electromagnetic observations. Converting redshift to cosmic time involves integrating the expansion history of the universe. At high redshifts, small differences in redshift correspond to substantial intervals of time because the expansion rate was faster. For example, the difference between redshift 10 and 11 corresponds to tens of millions of years. This sensitivity underscores the rapid pace of change during the cosmic dawn. Understanding the timeline helps contextualize when different processes occurred and how they influenced subsequent evolution. The fraction of baryonic matter, relative to dark matter, has implications for structure formation. Although dark matter dominates the mass budget, baryons are responsible for luminous structures. The ratio determines how much gas is available to form stars and influences the depth of gravitational potential wells. Variations in the baryon fraction across halos could affect galaxy properties, though in the standard cosmological model, the ratio is nearly uniform. Measuring the baryon fraction in clusters and galaxies tests models of cosmic baryon distribution and feedback. The rate at which gas is converted into stars is governed by the Kennicutt-Schmidt relation. This empirical law links the surface density of gas to the surface density of star formation. In high redshift galaxies, gas surface densities are higher, leading to rapid star formation. However, deviations from this relation can occur due to feedback, turbulence, and varying efficiency. Studying whether the Kennicutt-Schmidt relation holds at the cosmic dawn helps understand the universality of star formation laws. Star formation can proceed in bursts or in a more steady, secular fashion. In galaxies experiencing mergers or strong inflows, gas can be compressed, triggering brief but intense starbursts. After the burst, star formation may decline as gas is exhausted or driven out. Other galaxies maintain a steady rate, supported by continuous gas inflow along filaments. The balance between bursty and secular modes affects the observed properties of galaxies and their contribution to reionization. Metallicity often varies within a galaxy, creating gradients from the center to the outskirts. In the early universe, gradients may have been shallower because mixing was efficient in small systems. As galaxies grew, gradients became more pronounced, with centers enriched by successive generations of stars and outskirts supplied by more pristine gas. Measuring metallicity gradients at high redshift requires spectroscopy of individual regions within galaxies, a challenging endeavor, but one that informs models of gas inflow and outflow. The kinematics of early galaxies offer clues to their formation mechanisms. Some high redshift galaxies show ordered rotation, suggesting the presence of disks. Others are dominated by random motions, indicating turbulent, dispersion-dominated systems. The ratio of rotation to dispersion changes as galaxies settle and as feedback and mergers stir the gas. Detailed kinematic measurements using integral field spectroscopy reveal the dynamics of these systems and help distinguish between different evolutionary scenarios. Radiation pressure on dust grains can contribute to feedback by driving outflows. In regions with intense star formation, the combined radiation from many stars exerts a force on dust. This force can accelerate dust and the gas coupled to it, contributing to winds. Radiation pressure is particularly effective in galaxies with high dust content and star formation surface densities. Understanding its role relative to supernovae and stellar winds is important for modeling feedback processes. Cosmic voids, regions of space with low density, have unique evolutionary histories. Galaxies in voids experience fewer interactions and mergers, and may evolve differently than their counterparts in denser regions. They tend to be gas-rich and star-forming, with simple morphologies. Studying void galaxies provides insight into how environment influences galaxy evolution and offers a contrast to the more complex histories of cluster galaxies. In the early universe, voids were smaller, but still present, affecting the distribution of reionization bubbles and the growth of structure. Weak lensing measurements rely on detecting minute distortions in galaxy shapes, known as cosmic shear. The shear signal is small, and intrinsic shape variations of galaxies, shape noise, dominate the measurements. By averaging over many galaxies, the shear can be extracted. Accurate shape measurement requires careful modeling of the point spread function and control of systematic errors. Future surveys will increase the number of galaxies observed, improving the precision of shear maps and the constraints on cosmological parameters. Chronometers, like the ages of massive, passively evolving galaxies, can provide an independent measure of the expansion history. By comparing the ages of galaxies at different redshifts, one can infer the rate at which the universe has aged. This technique complements distance measurements and can cross-check the Hubble constant. Chronometers rely on accurate stellar population models and assumptions about galaxy formation history, but they offer a promising avenue for probing cosmic expansion. Time delays in lensed transients offer another route to cosmology. When a supernova or quasar varies in brightness, the delay between the images can be measured. These delays depend on the geometry of the lens system and the expansion rate of the universe. By modeling the mass distribution in the lens and measuring the delays, one can infer distances and the Hubble constant. This method is independent of other cosmic probes and provides a valuable cross-check. The cosmic neutrino background, relics from the first seconds after the Big Bang, permeates space today. These neutrinos are almost impossible to detect directly because of their weak interactions. However, their presence influences cosmic expansion and structure formation. Future experiments may detect the cosmic neutrino background through its impact on beta decay processes or capture on tritium. Such a detection would provide a direct glimpse into conditions just seconds after the Big Bang, complementing the story of cosmic dawn. The baryon cycle is intimately linked to cosmic chemical evolution. Outflows driven by feedback expel enriched gas, reducing the metallicity of the galaxy, while inflows of pristine gas dilute it. Recycled gas falls back into the galaxy after cooling, mixing with the existing interstellar medium. The timing and efficiency of these processes determine the buildup of metals and gas fractions. Observing the baryon cycle at high redshift requires sensitive measurements of gas flows and metal distributions in and around galaxies. Models of chemical enrichment depend on the initial mass function, the distribution of masses with which stars are born. If the initial mass function varies with environment or cosmic time, it could alter the rate at which different elements are produced. For example, a top-heavy initial mass function with more massive stars would produce more metals early on. Current observations provide hints, but no definitive evidence for such variations. Understanding whether the initial mass function changes remains a key question in linking star formation to chemical evolution. Morphological quenching is a process in which the structure of a galaxy suppresses star formation. In galaxies with large bulges or spheroids, the gravitational potential stabilizes the gas against collapse. Even if gas is present, it may not form stars efficiently. This mechanism can explain why some massive galaxies are quiescent, even though they retain substantial gas reservoirs. At high redshift, morphological quenching may have operated in some systems, contributing to the emergence of early quiescent galaxies. The cosmic star formation rate density has a distinctive shape over time. It rises from the cosmic dawn to a peak around redshift 2, known as cosmic noon, and then declines. This history reflects the interplay of gas supply, feedback, mergers, and environment. At early times, the abundance of cold gas and the hierarchical growth of structure drive rapid star formation. Later, depletion of gas reservoirs, heating of the intergalactic medium, and the exhaustion of gas inflow contribute to the decline. Charting this history is essential for understanding how the universe grew from simplicity to complexity. Cold streams of gas from the intergalactic medium play an important role in feeding galaxies. These streams flow along filaments, delivering relatively cool gas directly into the outskirts of halos without being shock heated to the virial temperature. In massive halos, however, gas can shock at the virial radius and form a hot halo that must cool slowly before accreting. This distinction between cold and hot modes of accretion influences the rate of star formation and the efficiency of galaxy growth. At high redshifts, cold streams dominate, enabling rapid buildup of galaxies. Chemical evolution of galaxies leaves fingerprints in the ratio of different elements. Elements produced by core collapse supernovae, such as oxygen and magnesium, are called alpha elements and are released promptly after massive stars die. Iron peak elements, produced by type Ia supernovae, are released after longer delays because they come from binary systems. The abundance ratio of alpha elements to iron therefore provides a clock for star formation history. High alpha to iron ratios indicate rapid star formation, while lower ratios imply extended or multiple episodes of star formation. Combining observations across multiple wavelengths enhances our understanding of cosmic dawn. Ultraviolet and optical observations reveal young stars and rest-frame ultraviolet light, while infrared observations trace dust-obscured star formation. Radio observations probe atomic and molecular gas, and X-rays reveal high-energy processes such as accreting black holes. By assembling data from many bands, astronomers build a more complete picture of galaxies, including their star formation rates, dust content, gas reservoirs, and black hole activity. This multi-wavelength approach is crucial for interpreting the complex processes at play. On smaller scales, streaming velocities between baryons and dark matter affect structure formation. After recombination, baryons were less tightly coupled to dark matter due to their residual thermal motion, resulting in relative velocities of a few kilometers per second. These streaming motions suppressed the formation of small halos and influenced the distribution of gas in the cosmic web. Including streaming velocities in simulations changes the predicted timing and scale of the first stars. Understanding this effect helps reconcile differences between theoretical predictions and observations. Some theories explore whether fundamental constants, such as the fine structure constant, have varied over cosmic time. Observations of absorption lines in the spectra of high redshift quasars test this by comparing the wavelengths of transitions to laboratory values. So far, no definitive evidence for variation has been found, but the results place stringent limits on how much these constants could have changed. Such studies connect cosmology to fundamental physics, probing whether the laws of nature are truly constant across space and time. Dust grains provide surfaces on which molecules can form. In the early universe, the formation of molecules like H2 and CO on dust could accelerate cooling in certain environments. Dust also shields molecules from ultraviolet radiation, allowing them to survive and participate in further chemistry. The presence of dust can therefore promote the formation of complex molecules and enhance star formation in enriched gas clouds. Understanding how dust abundance affects molecular chemistry is important for modeling the interstellar medium at all epochs. The next generation of observatories promises to push the frontier of cosmic dawn studies even further. The James Webb Space Telescope, now operational, observes the universe in infrared wavelengths with unprecedented sensitivity, uncovering galaxies at redshifts beyond 10. The square-kilometer array will map the 21-centimeter emission across cosmic time, providing three-dimensional movies of hydrogen gas. Euclid and the Roman Space Telescope will survey billions of galaxies, measuring cosmic acceleration and mapping the dark matter distribution through weak lensing. Together, these instruments will transform our understanding of the first billion years. Cosmic variance remains a challenge in interpreting observations. Because surveys cover limited areas of the sky, they may sample regions that are overdense or underdense compared with the cosmic average. This sampling variation can bias measurements of galaxy number densities, luminosity functions, and reionization timelines. Expanding the area surveyed and combining observations from different regions reduces cosmic variance. Accounting for it is essential for drawing robust conclusions about the universe as a whole. The universe serves as a laboratory for physics under conditions unattainable on Earth. The early universe reached energies far beyond those produced by our colliders, offering tests for theories of high-energy physics. Processes like baryogenesis, the matter-antimatter asymmetry, occurred then and left relic signatures. Observations of cosmic dawn complement these physics questions by constraining the number and properties of light particles, interactions, and deviations from standard models. Thus, cosmology connects the very large to the very small. Despite progress, fundamental mysteries remain. The nature of dark matter is unknown. Whether it is made of weakly interacting particles, axions, or something else remains a question. Dark energy, driving cosmic acceleration, is poorly understood and could be a cosmological constant or something more dynamic. These components influence the growth of structure and the timeline of cosmic dawn. By studying the early universe, we hope to glean clues about these mysterious substances and perhaps find new physics beyond current paradigms. Our curiosity about the cosmos is deeply human. As we learn about the formation of stars, galaxies, and structures, we also reflect on our place in the universe. The atoms in our bodies were forged in stars that lived and died billions of years ago. Our planetary home formed from dust and gas that cycled through multiple generations of stars. The cosmic dawn is therefore part of our own origin story, making its study not merely academic but profoundly personal. On the scale of hundreds of millions of light years, matter flows reveal coherent motions known as bulk flows. These flows arise from the gravitational pull of large-scale structures like clusters and superclusters. Measuring bulk flows helps to probe the distribution of mass and test theories of gravity. Observations of galaxy, peculiar velocities, can reveal anisotropies in the cosmic expansion and shed light on the growth of structure. Bulk flows at early times could have influenced the migration of gas and galaxies through the cosmic web. As the amount of data grows, new tools are needed to interpret it. Machine learning algorithms and artificial intelligence are increasingly being applied to astronomical datasets. These methods can classify galaxy morphologies, identify subtle patterns in the data, and predict properties based on multi-wavelength observations. By automating repetitive tasks and discovering hidden correlations, AI allows researchers to focus on formulating questions and interpreting results. The union of human curiosity and machine efficiency accelerates our exploration of the universe. Star formation efficiency varies with cosmic time and environment. In dense protoclusters, gas is compressed by gravity and interactions, leading to high efficiencies. In more isolated environments, gas may remain diffuse, and star formation proceeds slowly. Feedback, turbulence, and the influx of gas along filaments all modulate efficiency. Exploring how efficiency changes across the cosmic web improves our understanding of why some regions produced many stars early on, while others remained quiescent. Our narrative would be incomplete without acknowledging the role of serendipity in discovery. Many of the most profound insights into cosmic history have come from unexpected observations. A faint arc in a deep image turned out to be a lensed galaxy from the cosmic dawn. A slight dip in a radio spectrum hinted at 21 centimeter absorption from the first stars. Each surprise reminds us that the universe is not bound by our expectations, and that curiosity must remain open to the unknown. With each new observation, the story becomes richer and more nuanced. Patterns of star formation change not only from early to late times, but also from region to region. During cosmic noon, galaxies in dense environments formed stars vigorously, consuming their gas supplies and quickly enriching themselves. In contrast, galaxies in the outskirts of filaments or in voids could sustain lower levels of star formation over longer periods. These variations lead to diversity in galaxy properties observed today. Understanding this patchwork of star formation across the cosmic landscape helps to paint a fuller picture of how the universe evolved. As we weave through the tapestry of cosmic history, the threads of observation and theory intersect in intricate ways. The dawn we have explored gives way to midday and then to evening, each with its own rhythms of birth and decline. In the next chapter of our journey, we will witness galaxies maturing, clusters growing, and the cosmic web settling into familiar patterns. The light from those epochs still travels toward us, carrying stories yet untold. With patience and wonder, we continue to listen. The quest to understand the cosmos is an ever-evolving conversation between imagination and evidence. Each answer we find opens new questions, reminding us that knowledge is a horizon that recedes as we advance. In this pursuit, we become participants in the universe's story, not merely observers. Our curiosity binds us to the stars and to the ancient light that still whispers across space. Beyond the science, there is an emotional resonance to studying the cosmic dawn. When we look at the faint light from the first galaxies, we are looking back into a time before our sun, our planet, and our species existed. The atoms that make up our bodies were not yet forged. By connecting the story of chemical enrichment to our own origin, we feel a sense of connection to the cosmos. The cosmic dawn is not just a phase in astrophysical history. It is a prelude to the story of life. As we end this section of the journey, we pause to reflect on the enormity of time and space. The early universe was a place of both darkness and light, of simple elements and complex interactions. From tiny quantum fluctuations grew a web of matter spanning the universe. From the first stars came the seeds of chemistry and the light that rayonized the cosmos. These processes set the stage for everything that followed, including the galaxies, stars, and planets that populate the universe today. In our imagination, we might picture the cosmic dawn as a vast plain under a starless sky, slowly dotted by the first campfires of starlight. Those campfires grew, merged, and illuminated the landscape, revealing valleys and mountains, the filaments and voids of the cosmic web. Winds carried the ashes of those fires, enriching the soil with nutrients for future growth. Over time, the campfires became hearths and cities, galaxies and clusters, each with its own history. This poetic imagery underscores the unity of physical processes and the artistry of the cosmos. Looking forward, the story continues into epochs where galaxies coalesce into larger structures. Stars like our Sun form, and planetary systems emerge. The interstellar medium evolves from simple hydrogen gas to a complex soup of molecules, dust, and fields. Life arises on at least one planet, capable of looking back and piecing together this cosmic story. In the next part, we will explore these later chapters, tracing the growth of structure and the emergence of familiar cosmic landmarks. Our journey is far from over, and the universe still has many secrets to reveal. We pick up our cosmic story where the previous chapter left off, drifting away from the vast depths of the early universe and turning our gaze toward the familiar territory that surrounds us. In the slow hush of interstellar space, the light of our sun gives way to the dim glow of distant stars that share our region of the galaxy. The spiral arms curve like ancient rivers of stars, and within one of those arms lies the quiet cradle that we call home. Above and below us, the dark lanes of interstellar dust obscure and reveal the shimmering pattern of the Milky Way, reminding us that even our immediate surroundings are part of a much grander tapestry that reaches far beyond our imaginations. From the perspective of Earth, our solar system feels like a comfortable island, but it is only the smallest unit in a much larger hierarchy of structures. The Sun and its planets orbit within the disk of the Milky Way, a galaxy that stretches more than 100,000 light-years across and contains hundreds of billions of stars. Our galaxy is not alone. It belongs to a small gathering known as the Local Group, which contains dozens of galaxies of various sizes. The Local Group is dominated by two spiral giants, the Milky Way and Andromeda, along with numerous smaller dwarf galaxies that orbit them. These companions weave intricate paths through the gravitational dance of the group, tracing orbits that span billions of years. When we look beyond our galactic neighborhood, we find that the Local Group resides on the fringes of a much larger assembly of galaxies called the Virgo cluster. This cluster, in turn, is part of a supercluster of galaxies dubbed Laniakea, a Hawaiian term meaning immense heaven. Laniakea encompasses a region about 500 million light-years across and contains roughly 100,000 galaxies. Yet it is not held together permanently by gravity. Cosmologists have discovered that the accelerating expansion of the universe means superclusters like Laniakea are not gravitationally bound and will eventually be torn apart by dark energy. Our Local Group lies on the outskirts of the Virgo cluster and near the edge of Laniakea, making our cosmic address a place where the threads of the cosmic web are particularly delicate. The cosmic web resembles a vast network of filaments and nodes composed of galaxies, clusters, and diffuse gas. Gravity draws matter into this web, forming interconnected strands where galaxies accumulate like dew on spider silk, while between these filaments lie vast voids that contain very little. Dark matter is the scaffolding of this structure. It provides the gravitational well that ordinary matter falls into, giving shape to the filaments and nodes. Even though the voids are relatively empty, they still contain matter, including dark matter and diffuse gas. The cosmic web extends across the universe, and our local structures are just one small region of this grand lattice. To understand our place within the web, astronomers map the motions of nearby galaxies relative to the cosmic expansion. These motions are called peculiar velocities because they represent deviations from the uniform Hubble flow, the average expansion of space. The peculiar velocities of galaxies reveal the gravitational influences of massive structures nearby, much like the flow of water reveals the presence of hills and valleys in a landscape. By measuring these peculiar velocities, scientists have traced the direction in which our Local Group and its neighbors are moving. The data show that we and our neighboring clusters are streaming toward a region of space called the Great Attractor. The Great Attractor is a mysterious region located roughly 150 million light-years away, hidden behind the thick dust and gas of the Milky Way's disk. Astronomers first inferred its existence in the 1970s, when they noticed that nearby galaxies were moving toward a specific direction more quickly than the cosmic expansion could explain. It lies in the so-called zone of avoidance, a part of the sky obscured by our galaxy's bulge, making direct observation difficult. Infrared and X-ray observations have revealed that this region hosts the Norma cluster, a massive group of galaxies whose combined mass is around 1,000 trillion suns. Yet even this cluster cannot fully account for the acceleration of galaxies toward the Great Attractor, suggesting that larger structures further away are also exerting their pull. Beyond the Norma cluster lies a colossal assembly known as the Shapley supercluster. This region contains over 8,000 galaxies and boasts a mass exceeding 10 million billion suns. Observations show that the great attractor itself is being drawn toward Shapley, implying that Shapley is the dominant gravitational anchor in our corner of the universe. Newer surveys suggest that the Shapley concentration may extend even further than previously thought, forming a gravitational basin 10 times larger than the Laniakea supercluster. If this is correct, then our local group may reside within the outskirts of this vast basin of attraction, flowing inexorably toward a center whose nature we are only beginning to discern. Mapping these flows is like mapping watersheds on Earth. In a landscape, streams of water flow downhill toward basins and ultimately into rivers or oceans. Likewise, galaxies move through cosmic space, following the gradients of gravitational potential. The cosmic flows converge toward basins of attraction where matter has accumulated in greater density, just as rivers converge into valleys. Astronomers use the peculiar velocities of tens of thousands of galaxies to define the boundaries of these basins and to understand how clusters and superclusters form. This mapping reveals a dynamic universe in which we and our galactic neighbors are not static, but are instead part of an intricate, slow-motion migration across hundreds of millions of light-years. The concept of a gravitational basin evokes an image of a cosmic watershed, where galaxies like water droplets follow paths carved by invisible mountains of dark matter. It also illustrates how the present arrangement of galaxies traces back to tiny fluctuations in density present soon after the Big Bang. Over billions of years, these fluctuations grew under gravity, creating the filaments, clusters, and voids of the cosmic web we see today. As our understanding deepens, we realize that the structures we call superclusters may not be bound and long-lasting. Instead, they are temporary alignments, destined to be stretched apart as dark energy accelerates the expansion of space. In this view, our cosmic address is not fixed, but part of a continuous journey through an evolving universe. On scales smaller than superclusters, the flows of galaxies reveal the gravitational interplay among local structures. Our local group and the Virgo cluster are heading toward the great attractor, but they are also moving relative to each other. Andromeda is approaching the Milky Way at about 110 kilometers per second, and in roughly 5 billion years, the two galaxies will collide. This impending merger is part of the larger story of how galaxies grow through interactions and accretion. The gravitational dance that draws our galaxy toward Andromeda echoes the grander motion toward Shapley, connecting local events to cosmic flows. While gravitational attractions draw matter together, the universe also contains regions where matter is sparse. These are cosmic voids, vast volumes of space with lower than average density. Voids occupy most of the volume of the universe, making the cosmic web look like a sponge with dense filaments surrounding empty bubbles. Our local neighborhood may sit near the center of a very large underdense region, sometimes called the local hole or local void. Some astronomers propose that this void extends up to 1 billion light-years in radius and has a density roughly 20% lower than average. Living in a void has subtle effects on our measurements of the universe's expansion. Just as water flows out of a low-lying basin toward the surrounding hills, matter in a void tends to move toward denser regions. This gravitational outflow can cause galaxies within the void to have higher apparent recession velocities, making the local expansion rate appear faster than the global average. Such an effect could help explain the Hubble tension, the discrepancy between the Hubble constant measured from nearby galaxies and that inferred from the cosmic microwave background. Whether or not our cosmic address within a void fully resolves this tension, the idea reminds us that our local environment must be considered when interpreting cosmic measurements. Voids also leave imprints on the cosmic microwave background and on the distribution of galaxies. When light from the early universe passes through a low-density region, it experiences less gravitational redshift than light passing through a dense cluster, producing subtle temperature fluctuations known as the integrated Sachs-Wolf effect. Large voids could also produce cold spots in the microwave background, though the evidence for such features remains debated. By mapping the distribution of galaxies and measuring their velocities, astronomers continue to refine our understanding of voids and their role in cosmic evolution. In the quiet spaces between filaments, we glimpse the vast emptiness that makes the structures of the universe stand out in relief. As we move from the vastness of superclusters and voids to the more intimate scale of our own galaxy, we encounter the fossils of cosmic history preserved in stellar streams and dwarf galaxies. The Milky Way has not always been as it is today. It has grown through the accretion of smaller galaxies. Evidence of these mergers is written across the sky as long, thin streams of stars that trace the orbits of ancient dwarf galaxies torn apart by tidal forces. Each stream is a memory of a past encounter, a record of a smaller galaxy consumed by the Milky Way's gravity, leaving behind stars that still follow the path of their former host. These streams are time capsules, allowing astronomers to reconstruct the merger history of our galaxy and to test models of dark matter. Within the local group, dozens of dwarf galaxies orbit the Milky Way and Andromeda, but observations suggest that many more may be lurking, faint and difficult to detect. Simulations predict that the Milky Way could have up to 100 additional satellite galaxies, some of which may have been stripped of their dark matter halos and become so diffuse that they are almost invisible. These so-called orphan galaxies are predicted by models based on the lambda cold dark matter theory and are expected to be extremely faint, containing few stars and low surface brightness. The upcoming Vera C. Rubin Observatory, with its legacy survey of space and time, is expected to reveal many of these missing satellites, providing a critical test of our cosmological models. If the predicted satellites are found, it will strengthen the case for the prevailing theory of dark matter. If not, it may point toward new physics. Near-field cosmology is the study of the nearby universe as a laboratory for understanding cosmic evolution. By examining the detailed properties of stars and gas in the Milky Way and its neighbours, astronomers can infer the conditions that prevailed in the early universe and the processes that shaped galaxies. The chemical abundances of stars reveal when and where they formed, and stellar motions trace the gravitational potential of the galaxy. Stellar streams, dwarf galaxies, and globular clusters provide constraints on the distribution of dark matter. Gaps and perturbations in streams could reveal the presence of dark matter subhalos. Through this local archaeology, we gain insight into the larger-scale processes that built the cosmic web. Not all clues come from stars. Some lie in the faint glow that fills the universe. The extragalactic background light, EBL, is the cumulative light emitted by all stars and galaxies over the history of the universe. This glow spans infrared, optical, and ultraviolet wavelengths and carries the integrated signature of cosmic star formation. Measuring the EBL directly is challenging because foreground sources, such as zodiacal light and interstellar dust, are bright, obscuring the faint background. Instead, astronomers use high-energy gamma rays from distant active galaxies as probes. When gamma rays travel through intergalactic space, they can collide with EBL photons and produce electron-positron pairs, leaving an imprint on the gamma ray spectrum. The Fermi Gamma Ray Space Telescope has measured this attenuation, allowing scientists to infer the density of the background light at different epochs. By analyzing how the EBL changes with redshift, astronomers can reconstruct the star formation history of the universe. Greater absorption of gamma rays at earlier times implies that there was more starlight when the universe was younger. These measurements complement observations from deep galaxy surveys and help to resolve discrepancies between different methods of estimating star formation rates. They also provide constraints on models of galaxy evolution and the contribution of active galactic nuclei to the cosmic energy budget. The EBL serves as a diffuse record of all that has ever shone, a background hum of light that persists long after individual stars have faded. Listening to this faint whisper helps us build a holistic picture of cosmic history. Another subtle clue about the universe comes from the missing baryons problem. Observations of galaxies and gas clouds show that only about 2/3 of the ordinary matter predicted by cosmological models could be accounted for, leaving a significant fraction unobserved. Simulations have long suggested that the missing baryons reside in the warm-hot intergalactic medium, WHIM, a diffuse network of gas at temperatures between 1 and 10 million degrees. This medium, while hot, is so tenuous that it emits very little light and is difficult to detect. Yet it may contain much of the universe's normal matter, filling the spaces between galaxies like a faint, warm fog. Finding these baryons has been a major challenge, but new observations are finally bringing them into view. In recent years, astronomers have detected a 23 million light-year-long filament of hot gas connecting 4 galaxy clusters in the Shapley supercluster. This filament consists primarily of free electrons and protons at temperatures of more than 10 million degrees Celsius, with a density about 30 to 40 times the average cosmic density. Its mass is roughly 10 times that of the Milky Way. The discovery of this structure matches predictions from cosmological simulations, which suggest that typical WHIM filaments are less dense and hotter than those previously observed. This finding supports the view that most missing baryons are hidden in such diffuse filaments stretched across cosmic web. Another method for locating missing baryons involves using fast radio bursts, FRBS, as cosmic probes. FRBS are brief, bright pulses of radio waves originating from distant galaxies. As an FRB travels through intergalactic space, free electrons along the line of sight slow down the radio waves, causing a delay in the arrival times of different frequencies. This effect, known as dispersion, provides a measure of the total column density of electrons between us and the source. By analyzing the dispersion measures of FRBS at various distances, astronomers can estimate the amount of ionized gas in the intergalactic medium. Recent studies using dozens of FRBS have revealed that about 76% of the universe's baryonic matter lies in the diffuse intergalactic medium, with around 15% residing in the halos of galaxies and a small fraction locked up in stars and cold gas. These FRB measurements confirm that the missing baryons are indeed present, just difficult to see with conventional telescopes. In effect, FRBS act as cosmic flashlights, illuminating the fog of electrons that pervades intergalactic space. Because radio waves are not absorbed by dark matter and pass relatively unimpeded through the intergalactic medium, they provide a clean probe of ionized gas. By comparing the dispersion of FRBS at different distances, researchers can map how the density of baryons changes across the cosmic web. The results align with simulations, confirming that the WHIM contains the majority of the universe's normal matter. In the coming years, larger samples of FRBS will refine this census and help us understand how baryons cycle in and out of galaxies. Although these discoveries illuminate the cosmic web, they also highlight how much we still have to learn. the gravitational pulls of unseen structures, the whispering emptiness of voids, the ghostly traces of ancient mergers, and the warm glow of the EBL all point to a universe rich with hidden stories. Each new measurement fills in a small part of the picture, yet the picture grows more complex as we learn more. It is a reminder that the universe is a living, dynamic system, not a static backdrop. The flows of galaxies toward basins of attraction will continue for billions of years. The filaments of the WHIM will slowly become more diffuse as the universe expands, and the faint light of distant stars will carry the memory of cosmic history into the far future. When we look back to the cosmic dawn, we see the seeds that gave rise to the structures around us. Those seeds grew into the filaments, clusters, and voids that we inhabit today. The interplay of dark matter, baryonic gas, and cosmic expansion has shaped every level of structure, from the halos of dwarf galaxies to the Shapley supercluster. Our local group, with its 50 or so galaxies, sits on the edge of this vast cosmic architecture. The Milky Way and Andromeda dominate their immediate surroundings, but they are themselves part of flows that extend across hundreds of millions of light years, connecting us to the Great Attractor and beyond. The realization that superclusters like Laniakea are not gravitationally bound forever, but will ultimately dissolve highlights the transient nature of cosmic structures. Dark energy accelerates the expansion of the universe, stretching the cosmic web and thinning the filaments. Over tens of billions of years, the galaxies beyond our local group will drift so far away that their light will become faint and redshifted, fading into darkness. Only the galaxies bound within our group will remain visible, and cosmic structures like the Shapley supercluster will recede beyond our horizon. In this far future, the cosmic clues we explore today will become inaccessible, making our current era uniquely rich for studying the universe. As we examine the fossil record of the Milky Way, we see that the galaxy is shaped by interactions and mergers. The Sagittarius dwarf spheroidal galaxy is currently being torn apart, its stars strewn into a tidal stream that wraps around the Milky Way. The large and small Magellanic Clouds are interacting with our galaxy, producing trails of gas and stars that will eventually become part of the Milky Way's disk and halo. The streams reveal the gravitational potential of the Milky Way, and their disruptions may hint at the presence of dark matter clumps. Mapping these features not only tells us about our own galaxy's history, but also serves as a test for models of cosmic structure. Future telescopes will transform our view of the nearby universe. The Vera C. Rubin Observatory will survey the sky deeply and repeatedly, identifying faint dwarf galaxies, streams, and orphan satellites predicted by simulations. By combining these observations with precise measurements of stellar motions from missions like Gaia, astronomers will build a detailed map of the distribution of dark matter in and around the Milky Way. This near-field cosmology will connect the smallest scales of structure with the largest, showing how the cosmic web influences galaxy formation and how galaxies, in turn, reshape their environment. The interplay between local and global will come into sharper focus as the observational data grows. While the cosmic web is woven from gravity and dark matter, it glows with the light of ordinary stars. The EBL captures this cumulative glow across cosmic time, but individual galaxies contribute in different ways depending on their mass, age, and environment. Early in the universe, intense star formation produced a surge of ultraviolet and optical light, much of which has since been reprocessed into infrared radiation by dust. Active galactic nuclei also inject high-energy photons into the cosmic medium, leaving their mark on the gamma-ray background. By disentangling these contributions using gamma-ray attenuation and other techniques, scientists can better understand the life cycle of baryons and the growth of structure. The background light is like the sum of countless stories told at once, each star adding a whisper to the cosmic chorus. The idea of gravitational basins of attraction invites us to think of the universe as a dynamic landscape of hills and valleys carved by dark matter. In this landscape, galaxies are like raindrops rolling along slopes toward basins where they pool and accumulate. Each basin is defined not by a physical wall, but by the gravitational potential that guides the motion of matter. Our own path leads us toward the Shapley concentration, but we do not travel alone. Other groups, clusters, and even the great attractor itself follow similar trajectories toward this larger mass. The flows continue, even as the universe expands, demonstrating that gravity can momentarily overcome cosmic acceleration on small scales. However, the large-scale picture shows that dark energy will eventually dominate. As cosmic expansion accelerates, the gravitational pulls that shape the cosmic web become less effective. Over cosmic time, the basins of attraction will become less distinct, and the flows of galaxies will slow. In this future, the cosmic web will thin out, leaving isolated islands of galaxies surrounded by vast, empty space. Yet for now, we inhabit a universe rich with structure, motion, and opportunity for discovery. Understanding our nearby universe is not just about mapping our surroundings. It is also about appreciating the fleeting nature of cosmic structures. Our journey through the local universe reveals that even the apparently tranquil voids are humming with subtle processes. The warm, hot intergalactic medium fills the spaces between galaxies with gas heated by gravitational collapse and cosmic shocks. This gas carries metals, elements heavier than helium, expelled by supernovae and distributed by galactic winds. Over billions of years, the WHIM acts as a reservoir from which galaxies can draw material for new stars, and into which they expel the products of stellar evolution. Studying this medium requires sensitive X-ray and UV observations, as well as clever techniques like FRB dispersion measures. Each new detection adds another piece to the puzzle of how baryons cycle through the cosmos. The detection of WIM filaments, such as the 23 million light-year bridge in the Shapley supercluster, provides a direct glimpse of these structures. These filaments are not just strands connecting clusters. They are dynamic channels through which gas flows. Their temperatures and densities match the predictions of simulations, lending support to our understanding of cosmic structure formation. Measuring their metallicity and ionization state will reveal how far heavy elements have spread from galaxies into the intergalactic medium. In time, we may map out an entire network of such filaments, tracing the hidden arteries of the cosmic web. These discoveries remind us that even the empty spaces between galaxies are filled with complex, invisible matter. Fast radio bursts, meanwhile, have become one of the most exciting tools in modern astrophysics. Their origins are still a topic of active research, but their utility as probes of the intergalactic medium is unquestioned. Each FRB arrives with a characteristic sweep of frequencies due to dispersion, a signature that encodes the total number of electrons encountered on its journey. By measuring this dispersion and subtracting the contribution from our own galaxy, astronomers can infer the amount of ionized gas between galaxies. When dozens of FRBs are combined, the results reveal a detailed census of baryons in the universe, confirming that most of the missing matter lies in the warm, diffuse gas of the cosmic web. The idea that we might inhabit a large cosmic void adds another layer of intrigue to our cosmic story. If our region of space is underdense, the flow of matter outward could influence local measurements of the Hubble constant. Being at the center of such a void would make distant galaxies recede faster relative to us, leading to an apparent Hubble constant higher than the global value. Some observations of galaxy counts and supernova distances suggest that our neighborhood is indeed less dense than average, though the scale and impact of this void remain uncertain. Understanding our local environment is therefore essential for interpreting cosmological measurements and for resolving tensions between different datasets. All of these elements, the flows toward attractors, the presence of voids, the fossil streams of past mergers, the faint background glow, and the hidden baryons, are pieces of a larger puzzle. They demonstrate that the universe is interconnected across scales, with local phenomena reflecting global processes and vice versa. They also show that our cosmic address is both ordinary and extraordinary. We are one galaxy among billions, yet our journey through space is shaped by structures hundreds of millions of light years away. The delicate balance of gravitational pulls, cosmic expansion, and dark matter scaffolding determines where we have been and where we are headed. In contemplating these forces, we gain a deeper appreciation of the universe's dynamic and evolving nature. The story of our nearby universe is not yet complete. New instruments, surveys, and methods will reveal structures and phenomena we cannot yet imagine. The detection of faint dwarf galaxies will refine our models of dark matter. Improved measurements of the extragalactic background light will sharpen our understanding of star formation. Large samples of fast radio bursts will allow precise mapping of baryon distributions, and observations of cosmic flows will clarify the boundaries of gravitational basins, perhaps showing that the Shapley concentration is only one part of an even larger structure. As each thread is woven into the tapestry of knowledge, the picture becomes richer, but new patterns emerge that beckon us to look deeper. Even as we focus on our local cosmic neighborhood, we are aware that the universe extends far beyond. The flows we measure are only the beginning of a journey that leads to horizons where light from the earliest stars is stretched beyond detection. The cosmic microwave background, the oldest light we can see, carries imprints from a time when the universe was a hot, dense soup. The structures we observe today grew from tiny fluctuations in that soup. Understanding the connection between those early fluctuations and the present distribution of galaxies is one of the grand challenges of cosmology, and our local environment provides crucial clues. The interplay between gravity and expansion underlies the cosmic drama. Gravity pulls matter together, forming galaxies and clusters, while the expansion of space stretches them apart. Dark matter, though invisible, dominates the mass budget and shapes the gravitational landscape. Dark energy drives acceleration, making the universe expand at an ever-increasing rate. Our local universe is a microcosm of these competing forces. Watching how structures move and evolve within it allows us to infer the properties of dark matter and dark energy. The cosmic web is both a product of these forces and a laboratory for testing our theories. Observations of peculiar velocities, for example, can constrain the total mass in a given region and the growth rate of cosmic structures. By comparing the observed flows of galaxies with theoretical predictions, scientists can test models of gravity and dark matter. Similarly, the abundance and properties of dwarf galaxies depend on the nature of dark matter. If dark matter particles have different masses or interactions than in the standard model, it would affect the formation of small halos and the number of satellites. The distribution of baryons in the WHIM and halos is sensitive to astrophysical feedback processes such as winds from supernovae and active galactic nuclei. Each observation of our nearby universe thus informs fundamental physics. Even the orientation and shape of stellar streams can tell us about the gravitational potential of the Milky Way and the presence of substructures. Gaps in streams may point to encounters with massive bodies like dark matter, subhalos, or rogue black holes. The thickness and curvature of streams reveal the mass distribution in the Milky Way's halo. Because streams preserve the memory of their progenitors' orbits, they can be used to reconstruct past interactions and to predict future mergers. In this way, the fossils of the Milky Way become a record of cosmic archaeology, bridging our local environment with the larger cosmic history. Our journey through the local universe also reminds us of the interplay between the visible and the invisible. Many of the structures that govern the motions of galaxies cannot be seen directly. Dark matter is inferred from its gravitational effects. Dark energy is deduced from the accelerating expansion. The WHIM is detected not through direct imaging, but through its influence on X-rays and radio pulses. The extragalactic background light, while real, is hidden behind layers of foreground light and only indirectly measured by gamma-ray absorption. Our understanding of the universe is built from shadows and echoes, yet those clues are sufficient to reveal a richly detailed cosmic structure. The existence of the Shapley supercluster and the suggestion that it may be part of an even larger basin of attraction challenge our perception of scale. If our local group is indeed within a gravitational basin extending 10 times the volume of Laniakea, then our place in the cosmic web is even more peripheral than previously thought. The boundaries of such basins are defined by the interplay of gravity and cosmic expansion. They are not fixed walls, but evolving surfaces where flows converge or diverge. Mapping these regions requires surveys that cover vast volumes and measure galaxy velocities with high precision. The possibility of larger attractors invites us to continue pushing the limits of observation. As we look for the missing baryons and hidden structures, we also seek to understand the small differences between different measurements of the universe's expansion. The Hubble tension suggests that either our local environment or our cosmological model needs revision. The void hypothesis posits that living in a large underdense region could bias local measurements. Alternative explanations involve new physics beyond the standard model. The interplay between local and global, between environment and fundamental laws, is a theme running through our exploration. Each observation must be carefully interpreted in the context of where it is made, reminding us that our cosmic perspective is always tied to our location. On the scale of individual galaxies, we see that interactions can trigger bursts of star formation, feed central black holes, and rearrange stellar distributions. Tidal interactions with dwarf galaxies can warp the Milky Way's disk and excite oscillations in the halo. The Magellanic Clouds, for example, have left behind a stream of neutral hydrogen known as the Magellanic Stream, which arcs around the Milky Way and provides a record of their orbit. When they eventually merge with our galaxy, they will contribute their gas and stars, altering the Milky Way's structure and stimulating new star formation. In this way, the local environment is continually evolving, shaped by the inflow of material from its smaller companions. The interplay between star formation and the cosmic environment also influences the extragalactic background light. Regions with high densities of galaxies, such as clusters, may have different star formation histories than those in voids. The EBL integrates over all these environments, providing a global measure of the total star formation across the universe. By comparing gamma-ray attenuation in different directions, scientists may eventually map variations in the EBL and connect them to the distribution of large-scale structures. This could reveal how star formation is regulated by environment, and how feedback from galaxies enriches and heats the intergalactic medium. The faint glow that fills the universe carries more information than its uniform appearance suggests. The presence of baryonic matter in the WHIM also has implications for the chemical enrichment of the universe. Metals produced in stars can be carried into the intergalactic medium by galactic winds and supernova explosions. These metals then mix into the WHIM, enriching it and altering its cooling properties. Measuring the metallicity of the WHIM can therefore reveal how efficiently galaxies exchange material with their surroundings. The detection of metal lines in X-ray spectra of WIM filaments provides hints of this enrichment, though current instruments are at the edge of their capabilities. Future missions sensitive to soft X-rays will likely transform our understanding of metal distribution in the cosmic web. As we continue to measure the dispersion of FRBS, we will not only refine the census of baryons, but also explore the structure of magnetic fields in the intergalactic medium. Polarization of FRB signals can reveal the strength and orientation of magnetic fields along their paths. Understanding these fields is crucial because they influence the propagation of cosmic rays and the dynamics of plasma. Together with measurements of electron densities, magnetic field data will provide a more complete picture of the physical conditions in the cosmic web. The synergy of radio astronomy and cosmology promises to open new windows into the unseen universe, complementing optical, infrared, and X-ray observations. The concept of flows and attractors extends beyond the distribution of galaxies. It applies to the flows of baryons and energy as well. Gas flows along filaments into galaxies, where it cools and forms stars. In turn, energy and matter flow back out via stellar winds, supernovae, and jets from supermassive black holes. These feedback processes regulate galaxy growth and influence the surrounding medium. The cosmic web is thus a network not just of matter, but of continuous exchanges, with filaments acting as conduits for both inflow and outflow. Understanding these flows is crucial for a holistic view of galaxy evolution and the large-scale structure. Our cosmic neighborhood also hosts a myriad of transient phenomena. Supernovae explode in nearby galaxies, sending shockwaves through the interstellar and intergalactic medium. Gamma-ray bursts from distant galaxies cross our region, their high-energy photons attenuated by the EBL. Fast radio bursts flash unpredictably, their dispersion telling us about the electrons in our line of sight. Each event is a messenger carrying information about the environment it traversed. Together, they provide glimpses into the dynamic processes that constantly shape our universe. In contemplating the flows of galaxies and matter, we might also consider philosophical implications. Our notion of location becomes fluid when everything is in motion relative to everything else. The concept of a fixed address is replaced by a trajectory through an evolving cosmic web. The idea that our local group is moving toward a basin of attraction 10 times larger than Laniakea invites us to imagine scales of motion far beyond human perception. This perspective can foster a sense of humility and wonder, as we realize that our galaxy's path is part of a dance choreographed by forces acting across hundreds of millions of light years. Though we have focused on our local universe, the threads we pull inevitably lead to broader questions. How did dark matter come to dominate structure formation? What is the true nature of dark energy? Are there other fundamental fields or interactions that influence cosmic evolution? Each of these questions has implications for the structures we see and the motions we measure. Our study of the nearby universe provides boundary conditions and tests for theories, constraining the parameters of cosmological models. As we refine these models, we approach a more coherent understanding of the universe's past and its future trajectory. The interplay between observation and theory is particularly evident in the study of the EBL. The EBL encodes the integrated star formation rate, but the conversion from star formation to background light depends on factors like the initial mass function, dust content, and metallicity. Models of galaxy evolution must reproduce the observed EBL spectrum, which in turn constrains those factors. Similarly, the observed distribution of dwarf galaxies informs models of dark matter particle properties. By comparing the number of satellites predicted by simulations with those observed, we can rule out certain theories. The synergy between near-field cosmology and cosmological observations thus drives progress on multiple fronts. In the quiet darkness between galaxies, the WHIM may also host small populations of faint objects, such as ultra-faint dwarf galaxies and rogue stars. These objects are difficult to detect, but they could play a role in seeding further structure or in enriching the intergalactic medium. Some theories suggest that star formation could occur in filaments under the right conditions, though evidence for such events is limited. The discovery of orphan galaxies, satellites stripped of their dark matter halos and left as loose collections of stars, suggests that galaxy interactions can create unusual objects. Understanding these populations will help fill out our picture of the cosmic web's inhabitants. The local universe also offers an opportunity to study cosmic expansion in real time. By measuring how the velocities of galaxies change over decades, astronomers can directly observe the influence of cosmic acceleration. Such measurements require extraordinary precision, but they are within reach of planned instruments. Real-time cosmology could reveal subtle variations in the Hubble flow across different directions, perhaps linked to structures like the Great Attractor and the Shapley concentration. This would provide a direct test of the isotropy of cosmic expansion and the uniformity of dark energy. The prospect of watching the universe expand before our eyes is as breathtaking as it is challenging. As the cosmic web evolves, the boundaries of our local region will change. Some dwarf galaxies will fall into the Milky Way and disappear as distinct entities. Others will be flung to greater distances by gravitational interactions. Streams of stars will lengthen and fade, their progenitors long gone. New voids may open as matter flows out of underdense regions. This continuous change reminds us that the current configuration of our neighborhood is temporary, a snapshot in a long movie. Understanding the flows and structures present now allows us to predict what our region will look like in millions or billions of years. The interplay between the cosmic web and galaxy formation also shapes the distribution of angular momentum. Filaments channel gas and galaxies into clusters along preferred directions, influencing the spins of galaxies and the orientation of their disks. Observations suggest that galaxies embedded in filaments have correlated spins and alignments. This alignment may extend to the level of superclusters, linking the orientation of galaxies to the overall structure of the cosmic web. Such correlations provide another avenue for testing theories of structure formation and for exploring the role of dark matter in shaping angular momentum. Another fascinating aspect of our local universe is the interplay between supermassive black holes and their host galaxies. Black holes at the centers of galaxies can influence their surroundings through powerful jets and winds. These outflows can heat and expel gas from galaxies, regulating star formation and affecting the WHIM. The energy injected by active galactic nuclei propagates along filaments and into voids, altering the thermal state of the intergalactic medium. Understanding how these feedback processes operate in different environments within the cosmic web is crucial for building accurate models of galaxy evolution and the background radiation fields. Looking ahead, the coming decade promises significant advances in our understanding of the local universe. Surveys like Euclid and the Nancy Grace Roman Space Telescope will measure the distribution of galaxies and their shapes across large volumes, providing new insights into cosmic acceleration and the growth of structure. The Square Kilometre Array will detect thousands of new FRBs, enabling precise mapping of baryons and magnetic fields. Ground-based telescopes will uncover faint dwarf galaxies and map stellar streams in unprecedented detail. Each of these projects will build upon the foundation laid by current observations, adding layers of richness to our cosmic narrative. Through all these explorations, a sense of wonder endures. The vast emptiness of voids, the hidden clusters behind the Milky Way's bulge, the faint whispers of gamma rays attenuated by background light, and the fleeting flashes of FRBs all serve as reminders that the universe is full of mysteries waiting to be uncovered. Our journey from the cosmic horizon to our local neighborhood has shown us that even the familiar can be profound when viewed in the context of the larger cosmos. Every star, galaxy, and filament is part of a grand tapestry woven by gravity, dark matter, and time. By studying our nearby universe with care and curiosity, we not only understand our own place, but also glimpse the deeper workings of the cosmos. The story continues as we turn our attention outward once more, ready to explore what lies beyond the edges of our visible horizon.